First of all, I want to thank Professor Chen for the invitation, and also for all the faculty, students, volunteers, and also the friends from the industry for organizing this wonderful conference. Okay, this is my first time to visit Tsinghua University. I'm so impressed by everything I have seen so far, and it's simply amazing. Okay, so let me go back to my talk. So my talk today is about matrix clustering problem. Okay, so this is a joint work with two of my students, Yingben Li, who is a postdoc at the Chicago booth, and Si Yideng, who works at Amazon. Okay, so clustering is a well-known unsupervised learning problem, and it has a lot of literatures and tons of applications. So today I want to touch a slightly less explored topic in clustering called the matrix clustering problem. Okay. So in particular, we focus on the following setup. So we assume we have n ID copies of the random matrix X, which is a P by Q random matrix. Okay. Our goal is to find the clusters of this random matrix, or random feature matrix X. Okay. So this is different from a lot of clustering problems. For example, it's different from the data clustering. Okay, for example, you can do Gaussian mixture model. That's a typical model for data clustering. Okay, you have heterogeneity among samples, right? It is also different from the classical back clustering problem. So in the back clustering problem, usually we have a data matrix, which is n by q or n by p. So the n stands for the samples, and the p stands for the features. In some sense, the back clustering cluster both on the sample level and also on the feature level, okay? But here, our data matrix, or the feature matrix X, they are all the features, okay? And we have extra NID copies. Okay, so there are other clustering problems like the network clustering, etc. They are also different. Okay, so to solve this matrix clustering problem, so we need a statistical model for that. Okay, so what is the statistical model, or how to define clusters in this problem? That's one question we need to address. So the second question is, what are the statistical guarantees, or especially the optimality in the minimax sense? Okay, can we show that? Okay. So for whatever matrix value data we have, the first question we may ask is, why not just vectorize the feature matrix as a vector, a long vector, right? So here I show you a simple experiment that basically says what you can obtain if you do this vectorize the data, or if you use a proper, right, a proper matrix clustering problem, matrix clustering algorithm. Okay, so you can say if we just vectorize the matrix and put it a long vector, and we run whatever like vector clustering method you like. Here I have one particular method. Okay, this is the clustering pattern you can observe. You can say there's no clear pattern. In other words, the results are not interpretable. On the other hand, if we run a proper matrix clustering algorithm, so you can say, well, we have clear row clusters and also clear column clusters. Of course, this is after arrangement, right? After what we obtain from the algorithm, and then up to a rearrangement, right? You can say there's a clear pattern, and the results become more meaningful. Okay. Sure. So this is basically one. You can think about this as a population level in some sense. This is the here is actually have a concrete example. For example, here that's the column. This is a row. Maybe I should flip this. Okay. So for example, this column may represent genes. These rows may represent tissues. So in some sense, you have one sample that is gene by tissue, gene expression levels. That's what you can see in the next slide. That's kind of a motivating example. And you have NID copies of this type of matrix. You want to recover this pattern, right? Well, uh, I think this is generated from the same model. First of all, data are generated from the same model. And here, okay, clearly if you vectorize the matrix, you basically ignore the matrix structure. So in other words, you can say there's the clusters, right? Okay, they do have cluster structures, but you won't have a clear, like this type of block structure, right? If you have row cluster and column clusters, you will have some block structure in the matrix. Here, you just have a number which is the same, and you can say they are the same cluster, but this no longer form a block, right? Okay. Okay. You lose the matrix structure. Yes, in some sense, you do not fully utilize the structure of the data, right? Okay. Okay, so let's move to the. This is a matrix, right? So you have 20 by 20 matrix. Okay, so ideally you should have 20 by 20 numbers, right? Okay, and then you have n ID copies of this type of random matrix. Okay, of course I color that for better visualization, right? Okay, and as I said, this is the population level in some sense. Okay, on the sample level, you will have all those numbers, and you run the matrix clustering algorithm, and you want to recover this pattern. You can say the pattern with block structure, right? Of course, this is after a rearrangement, right? When you run the algorithm, they won't say, well, this from one row or one column cluster, right? Maybe this row should be here, or this row should be here, right? I get it back after rearrangement, right? So my point is, if you use the matrix structure properly, you can find more informative patterns from the data, okay? I mean, mathematically, you should still recover similar things by vectorizing data, but they are not fully informative, okay? And by the way, I think we use a very small sample, maybe like n equals 10 or 20. That's why you can see big difference, right? Okay. Okay, let's move on, and we can, any other question, I can address it after offline, okay? So here is just a data example, as I said. We use our public data. This is typical data for matrix valued problem. And these are gene expressions for n equals 36 mice. Okay, that's the sample size n. And for each mouse, we measure their gene expression. So we have over 8,000 genes across Q equals 16 tissues. Right? So each mouse will have a P by Q data matrix, and we have 36 this type of random matrices, right? And our goal is to find the cluster of rows and columns. In other words, we want to find the gene cluster and, and also tissue clusters. Okay. So here are some results I get. Of course, there should be more genes in each cluster. There should be more clusters. I just pick some for illustration, and also this for the tissues, right? Okay. And we say, well, this result makes biological sense, and this I have some detail in the paper, so I will skip that. Okay. So this is what you can get by using our type of method. Okay, so in today's talk, I will introduce a factor model for matrix clustering, and also we talk about how to derive the algorithm by using this covariance difference, and we also show some theoretical results like optimality and consistency, and finally we use that method to solve a matrix normal model. Okay. Okay, so let's start from the model. So that's the first line is just a setup, right? So the factor model we use is very simple. So we assume that X, this random matrix X, can be decomposed into two parts. The first part can be called as a signal. The second part, gamma, is a noise. So the signal, there's a Z matrix. So the Z is actually a mean zero latent factors matrix. Usually you have latent vector, but now you have a matrix, okay? And the gamma are noise, and assume some independent structure makes the calculation easier. Okay, so here I say this K1 and K2 denotes the number of row and column clusters. In some sense, the clustering structure is driven by these latent factors, okay, by latent factors. And to make the model rigorous, in clustering literature, we usually introduce a so-called membership matrix, right, to denote the cluster label. And here I introduce the A will be the row-wise membership matrix, okay, which is a P by K1 matrix. Here's just an example, right? So suppose our data X has 4 rows, so P is 4. And K1, I only have 2 row clusters. You have 2 row clusters. And then clearly, the first 2 rows form the cluster 1. So the last 2 rows is cluster 2. You can say this membership matrix tell you the clusters, right? In other words, our goal is to recover this unknown membership matrix A and B. I should mention the B is a column-wise membership matrix, right? Defined in a symmetric way. Okay, that's the model. Okay, so how to recover A and B? So let's start some calculation on the population level. Okay, so we look at the so-called covariance difference or weighted covariance difference. Let's for now mostly focus on row clustering. Okay. So the first thing we observe is since everything has mean 0, so we can say everything has mean 0, so Z has mean 0. In other words, the mean of Z, or the data, doesn't carry over any information about the clustering, so we have to go to the second moment, which is the covariance. Right? So that's why we compute the covariance, but because X is a matrix, right? So we actually calculate this weighted covariance, and this sigma PW will be a P by P. Okay, it's a P by P matrix. It's some type of covariance for rows. Okay? If you do simple calculation, this is what you get from the independence. So one important observation is the following. If we look at 2 different rows, A and C, they are 2 different rows. And say A belongs to row cluster K, C belongs to a different cluster L. And we look at the A6 entry of this covariance matrix, okay? And this guy will have 0 because I have some independence assumption. So I only have the AC component from the first term. And recall that the A is a membership matrix, right? It can locate the cluster label. If you look at the corresponding row, it locates the cluster label. So it reduced to K and L. Okay. That's because A is a membership matrix. In other words, if we just look at the A6 entry, essentially it's driven by the cluster label, right? Okay. It depends on the cluster label where A and C belongs to. Okay, so from this calculation, okay, we actually can show the following result. Okay, so here we do need some actual clustering separation condition, which will be more clear in the next slides. Okay. And it says if A and B belongs to the same row cluster, it belongs to the same row cluster, then these 2 numbers should be the same for any C different from A and B. Okay. So from left to right is straightforward based on this observation, right? If you have, here I already calculated AC, right? I can similarly calculate the BC. If you plug in BC here, you do the calculation, you get same thing, right? You get same thing because A and B belongs to the same cluster. So from left to right, they're straightforward, right? But from the right to left, you need some additional assumption. Basically, it says the different clusters should be different, right? And that's why we can introduce so-called a minimal covariance difference or minimal weighted covariance difference, the MW chord. So essentially, you look at the difference between the two quantities in the previous slides. Okay, you look at the maximum over all the C different from A and B. Okay, so here it equals for any C different from A and B, right? If they belong to the same cluster. So to make the difference bigger, I look at maximum over C, but also I will take the minimum for all the rows or pairs A and B not in the same cluster, okay? Because we know if A and B in the same cluster, this quantity will be 0, right? So if A and B belongs to the same cluster, it becomes 0, and if they are not in the same cluster, if it is greater than 0, then we can clearly tell, right, which variables should be, they belong to the different clusters, right? Okay, we can basically tell the clusters. So if we are assuming this quantity is bigger than 0, then we can argue, well, this membership matrix A is identifiable up to label switching. So this is more like identifiability result on the population level. Okay. Okay. On the sample level, we may say, well, maybe we should plug in some sample estimators of this matrix and do something similar. Okay. But on the sample level, it's a little bit more tricky because if we kind of rescale the weight matrix W, okay, or the data X, say we make X to be 100 or 1,000 times X, so this covariance matrix will be bigger. So you can always make this, this guy diverge in some sense. Okay. So in other words, on the sample level, we need to find a way to standardize this metric. Okay. So that's why we consider this so-called standardized MW chord, which is basically this same thing divided by a quantity that depends on the matrix W and also the covariance matrix of X. And so the form is actually inspired from the technical proof in our result. So this is the most convenient one for our proof, but it works. First of all, it works in theory and reasonably good in practice, but this may not be the only way to standardize the, I think, this metric. Okay. Okay, so this is what we propose to use. So this standardized version of core, so I call this delta S. Okay, so the S stands for the standardization. Okay. Okay, so basically this delta S measures the cluster separation per unit variance of X. Okay, because the denominator depends on the variance. Okay, so I think I think I should still keep this. Okay, so what we can do in practice. So in practice, we can simply find an empirical estimator of the covariance, and then we should try to compute a sample analog of the previous standardized version of chord. So of course, okay, you do it for each pair, A and B. Okay, you look at two different rows, A and B, and do this calculation. Okay, and the last step is once we have all these quantities, we will run some whatever cluster, hierarchical clustering algorithms. Okay, for example, the one in the R package, and to basically get the result. So more precisely, what we do is we merge those two clusters I and J together, if and only if this measure is below a threshold alpha, okay, for any A and B. Okay. And finally, we get a cluster estimate that's A hat. Okay. So this is the algorithm, okay, the main algorithm. Okay. Okay, so I think another thing I should talk about is what is the weight matrix W. Okay. So there are different choices of the weight matrix W. So here, identity matrix, that's a simple one we can use. And a more interesting one is the second choice called denoising matrix or denoising weight, which looks a little bit strange. Okay. But the motivation for using this weight is from the following calculation. Okay. So here we have X star. So the X star is basically average of the column in the same cluster. So recall that your data has a P by Q. You have Q columns, but you are K2 column clusters. So what you do is you average all the columns in the same cluster, right? You compress this Q column into K2 columns. Okay, you compress into K2 column and compute the weighted average covariance matrix across these K2 columns. So it turns out it has, using this denoising matrix, it has better performance and theory. Okay? So here is just a simple example. It shows under some conditions, right? If you look at what we get from this two matrix decomposition, you get same term signal, okay, same term signal, but the noise term will be different. In particular, if you use a denoising matrix, so the noise term here is reduced. That's why we call this as a denoising matrix. Okay, it boosts the signal, reduces the noise in some sense. Okay, so well, you may realize this this WO, the denoising matrix, depends on the unknown column cluster B. So in some sense, this motivates us to run this iteration algorithm, right? So you first do clustering for rows, find initial value, do clustering for rows, and then you get some column cluster, row cluster estimate, and then you do column clusters, right? And you may further iterate row plus column, right? Okay. So this actually motivates us to develop a iteration algorithm, okay? Okay, so here I think I will briefly talk about some theory. Most of the notation we have seen before. So only the last one, so this is the delta bar S. So we introduced this because we have an initial estimate or initial value for the weight WO. Okay, we call this W bar, then everything become bar, right? Everything become bar. So our main result says, we need mainly two conditions. One is the cluster separation condition. In some sense, our standardized MW core should be above this level. Notice that this term decreases with the sample size n, that's expected, but it also decreases with the number of column cluster K2. If you have more column cluster, it actually helps you to cluster rows, okay. So that's one like a unique phenomenon in this matrix value data. So this K2 show up here. And also we need a stability condition, which basically says our initial value should not be too bad in some sense. And under these two conditions, we get row clustering consistent with high probability. And also we can give a lower bound result, basically says for any level below this threshold, for any level below this threshold, there's no consistent row clustering algorithm. So in some sense, this is the minimax optimal rate for matrix value clustering problem. Well, I think that's probably my last slides. I do have one more for simulation, but I don't think I have time. So here we see two main conditions. One is a cluster separation. The other is stability condition. So they are more like high-level condition. You may argue, well, what the condition looks like in a specific model. Here is a specific model. It's a matrix normal model. So we further assume this latent factor Z follows a matrix normal model. The first line, that's our actual assumption, And the second line, that's a mild regularity condition, right? Some eigenvalue and bounded entries, right? So it turns out a sufficient condition for cluster separation, is the following, right? So intuitively, this simply means if you look at this row-wise covariance matrix U, okay, there should not be two nearly identical rows, right, of U. Otherwise, your U matrix, covariance matrix becomes singular. This is no longer a valid covariance matrix. Of course, it should be above this level, so it makes this rigorous, right? That's more like a very mild condition, okay? So what would be the stability condition? It depends on the initial value. So it turns out you get a very clean result under some extra condition. I have more general condition in our paper, but let's focus on a clean result. So if we assume homogeneous noise, and also we assume the column cluster size are balanced, and there are some more variables in the same cluster, it's kind of the actual condition, right? So surprisingly, we can show the stability condition holds for B bar equals just the identity matrix. In other words, you can initialize your algorithm by putting each column as its own cluster, right? Just treat all the column, Q cluster. That's the initialization you can do in this model, and it works, okay. Okay, so we have some simulation. I think I will skip that, okay. So here is just a summary. So in this talk, we focus on a factor model for matrix clustering problem, and we consider algorithms and derive all the theory consistent with the minimax optimality. And we could relax some assumptions. For example, independence noise assumption, we can relax those assumptions. There are definitely more work we can do along this line. For example, okay, there's first of all, we can consider some adaptivity problem. So one problem actually Ravi asked is clearly this choice of the threshold alpha depends on the unknown column cluster K2, so the algorithm is not adaptive, so we can consider how to make it adaptive, and also we can consider other problems like tensor clustering problem or cluster with overlaps, right? So these are the possible extensions, and I'm running out of time. Thank you everybody for attention. So the bi-clustering, typically you have the data matrix, and usually most of the, I would say most of the clustering problem, their clustering information is carried by the mean, right? You have the x equals the mean of x plus some noise, and you assume the mean has some particular structure, like whatever bi-clustering or block clustering structure, right? And you run whatever method to find these blocks, okay? But here our model, in our model, our information is carried by the covariance, okay? So in some sense, we have to look at the covariance and try to study the covariance structure of the model and derive the algorithms. So you can say we do use some bi-clustering type of algorithm, like hierarchical algorithms, right? But you have to apply the algorithm to the right quantity to get to recover the clustering structure. Yes. The goal is more like, yeah, you can just modify or twist the bi-clustering problem to apply to our problem. Yes. Yes. Yeah. Right. Oh, yes. Right. Yes, so in our algorithm, we do not assume we know the number of clusters, right? So the tuning parameter in our algorithm is a threshold alpha, which of course theoretically depends on some K2, okay? Usually in practice, we just use cross-validation to find alpha. So we don't need the exactly value of cluster, yeah, the number of clusters in our algorithm. Yes, thank you, a good question.
时间原因，我们请下一位speaker 是我们下。 我们下一位 speaker 是来自 Temple 大学的赵志根教授，他是康奈尔大学的数学 PhD， 他现在是Temple University Department of Statistics Operations and Data Science Associate Professor， 他是 elect member of ISI。赵教授的研究兴趣包括 sufficient dimension reduction, Bayesian, empirical Bayesian statistics, high dimensional data analysis, multiple comparison bioinformatics and selective confidence intervals。让我们欢迎他给我们报告testing exchangeability。你这个上面吗？
谢谢吴教授的introduction 还有谢谢刘老师这次邀请我来清华参加这个会议之前我清华这边有蛮多的朋友以前也经常来，去年的时候我也过来了，今年又回来了，每次过来都能够感受到清华日新月异的变化，在刘老师的带领下，所以我在这里感受到了清华速度。然后另外就谢谢组织方这次安排这次会议，然后来到这个雁栖湖这个非常漂亮的地方。然后对于我们这种，我是一个马拉松跑者，对于一个跑马拉松的人来说，一个大湖周围有一个跑道，这是有着一种不可拒绝的魔力。但是我昨天来的时候发现我没有带鞋，所以当时肠子都悔青了。到这的时候肠子都悔青了。后来在崇新老师的建议下，然后又感受了一把中国速度。然后临时在美团上面买了一双跑鞋，昨天送到宾馆，然后今天早上穿着鞋到外面去跑了一圈，感觉真是非常非常漂亮。今天外面下了小雨，烟雨蒙蒙的，就跑步的时候，就马上就想到了苏轼的那一首《定风波》那一首词，叫莫听竹林打叶声，何妨吟啸且徐行，竹杖芒鞋轻胜马，休怕一蓑烟雨任平生。当时跑的感觉简直就像人间仙境一样，但是呢，跑的时候有多爽，回到宾馆的时候就有多惨，回来的时候全身都湿透了。所以当时这里又要特别感谢我们的那个sponsor， 黄大华茶务会是吧？黄大华茶苏不仅给我们提供了这么好的开会的地点，而且还贴心的为我们准备了一件 T 恤，穿上身上特别舒服。好，就现在我们言归正传今天我想给在座的各位老师汇报一下我们最近的一个工作，就 testing of the exchangeability。This is a joint work with my student Tian Yu and my collaborator Kai Zhang from University of North Carolina and Dr. Zhou Wen from New York University. Okay. So this problem is actually a very, very classical problem without any further introduction. So it's a very classical. So let x1, x2 to xp, this is a random vector. And then a very natural question that people have asked maybe 100 years ago is like, so whether these xi's are independent, whether they're all independent, like mutual independence, or sometimes we can consider block independence. So testing of independence, this problem has been studied very thoroughly in the last century. And then if they're not independent, then the next question we can ask is what kind of dependent structure that this random vector has. And then the next question we were trying to answer is whether these xi's, they are exchangeable, so if they are dependent. So exchangeability, actually, this is also a very important problem. And this is the famous definity theorem, which tells us that for a sequence, if this infinite sequence which is exchangeable, so it means that there will be conditional independence. So exchangeable, this is a very fundamental condition for many statistical modeling, especially in the Bayesian statistics. And also nowadays, actually, in the conformal analysis and some other methods, exchangeability, this assumption has been very widely used. So, but for this problem, actually, that how to test exchangeability, this problem is not sufficiently investigated. So this is the list of the methods for the testing of independence. So we can see that the testing independence has been very thoroughly investigated. And so some of the literature goes back to like more than 100 years ago. And the recent one, including 2019, and even from facial exact scanning methods, and also recently had the BAT and BEAST. So this paper has been introduced in the last 2 or 3 years. Yeah. So we can see that there are all literatures across different years, and people introduce different methods. There are very novel methods in different years. About testing of the exchangeability, we can see that literature is actually is much less than the testing of the independence. So we're just listing a few methods here. So we shall have some people use rank-based test, some people use permutation-based test, and then there are some other moment-based methods in the category of other tests. Yeah. So we can see that for this two testing problem, actually, the people are using two totally different way to tackle the issues. Yeah. So now we want to ask the following questions, and the first one is that we want to unify these two methods, the testing of independence and the testing the exchangeability, under one unified framework. And the second one is that we want to introduce a method which can test the exchangeability adaptively. Yeah. So for the rank-based test and the permutation test and the moment-based test, and for those tests, sometimes they work very well, but for some other cases, they failed completely. Okay, so we want to introduce some adaptive way to test this exchangeability with a good power. Right? Okay, so what is the framework we are going to use? It's called the binary expansion test. Okay, binary expansion test. So this will be the outline of my talk today. And firstly, we want to give an introduction about the binary expansion test. And especially, we want to study the characteristic function of any random vectors. Yeah. So we can see from here that this method will be purely non-parametric. So we do not need to assume any distribution assumptions. Yeah. And second one, we want to introduce a binary representation of the random variable with exchangeability. And the acronym, we call this brevity. Yeah. And then we introduce a data-driven method and followed by some numerical studies and hope for some real data analysis if time permits. Yeah. So firstly, we want to introduce a binary expansion framework. Yeah, so we start from any numbers. Yeah. So if this number is folded into the interval from -1 and 1, okay, then we can consider the binary expansion. Yeah. So usually we are familiar with the binary expansion when the number from 0 to 1, right? And then all the digits will consist of either 0 and 1. And this is very connected, strongly connected to the computers, right? Computers. But then we use -1 instead of 0 just for some technical convenience. Yeah. And for any numbers, we know that this can be, how to go back to the screen mode? So for instance, if we use any number -0.3875, then we can use a binary expansion. So we can use the -1 and 1, these digits, to represent these numbers. And then if you use a random variable with the support from -1 to 1, then we can do a similar thing. And then we can write U in terms of the binary expansion. For instance, if Uj is any random variable from -1 to 1, support -1 to 1, then Uj can be written as the sum of AJD over 2 to the power of D. So AJD, this random variable, this is bivariate random variable, which can take only two possible values, either -1 or 1. Okay, it's like a Bernoulli random variable. Right? And then we can truncate this random variable up to the depth of T. Okay, we can truncate. And then we can show that when D goes to infinity, and this binary approximation will converge to the original random vector almost surely. Yeah. And then the distribution property of the original random vector can be approximated by this binary interaction. And then for the binary interaction, then these are just conserved digits. And then study the binary interaction, this binary approximation will be much easier. Yeah. So this can be treated as multinomial distributions. Okay, the multinomial distributions, and then for the multinomial distribution, we know that there's sufficient statistics will be all the other ratios, and all the other ratios can be represented by these binary interactions. So this product of all the AJDs. So this will give us full knowledge about these original random vectors. Okay, so all the study of the original random vectors can be converted to the study of the binary interactions. Yeah. Okay, so for the binary interactions, then we introduce some notations. So we use this lambda, which is a matrix, P by D matrix. And this matrix has all the entries of being either 0 or 1. Right? And then we introduce A of lambda. So A of lambda, so basically we just pick up a set of AJD and then put them all together. Okay, and then we call this the binary interactions. Yeah. And psi lambda t, this is a trigonometric polynomial of the trigonometric functions, which serves as the basis. Yeah. For instance, when we p equal to 2, and we have two-dimensional case, and the depth is chosen as 3, and lambda 0, 1, 1, 1, 1, 0, this represents one binary interaction. So in this binary interaction, we just put the second binary digits from second and third binary digits from the first random variable, and the first and second binary digits from the second random variable. Then we put them together. So this gives us one binary interactions. And then if we go through all these lambdas, then we can go through all these possible binary interactions. Okay. Then we have a very beautiful theorem. Yeah. And this theorem we give the name as beauty. Very beautiful theorem. And then if you appear any p-dimensional random vector with the support of -1 to 1, and then we consider characteristic function. So this characteristic function can actually be written as the limit when the depth goes to the infinity. And this is sum across all these binary interactions. So this is the trigonometric functions, and this is the binary interactions. So we can see that if we want to understand this random vector U, so then if we know the characteristic function, then we know everything about this random vector. And how do we know this characteristic function? We only need to know the expectation of A lambda. So as long as we know the expectation of all the binary interactions, then we know these random vectors. Okay. And this is we call this is binary expansion approximation of the uniformity. Yeah. And this applies to any random vectors without any distributional assumptions. Okay. And by the way, we can also show that this psi lambda t, this trigonometric polynomial, they are linearly independent. Okay, they're linearly independent. Okay, so that's our first paper. We introduced this. Beauty formula. So now we want to apply this beauty, the binary expansion test, into the random variable with exchangeability. Right? So what is exchangeability? What is exchangeable random vectors? Right? So so basically it means that we consider distribution functions of this random vector, and this distribution function is invariant with respect to any permutations. So we let M, this is a set from 1 to P, and SYMM, this will be the symmetry group of this M. Okay. And now we know the random vector is exchangeable, and if this distribution function is invariant for any permutations. Okay, so then we have a theorem which shows that if p-dimensional random vector is exchangeable, then for any sigma, which is a symmetry, this is the permutation from symmetry group, and then the characteristic function of phi u of t, and this will equal to the characteristic function when we do the permutation of this argument t. Yeah. And this condition is equivalent condition, so the converse is also true. Okay. So now the next one, we want to connect that result with the beauty formula. Right? And here we want to introduce some relationship between all these binary interactions. Okay? We want to define an equivalent relationship in the set of all the binary interactions. So we have lambda 1 and lambda 2. And then we call that this lambda 1 and lambda 2, they are equivalent if we are able to apply a row permutation on the one of this binary interaction, then we get the second one. Then we call these two interactions are equivalent. For instance, for this lambda 1 and lambda 2, we can just permute the second one and the third one, the second row and the third row, then we get lambda 2. So we call this lambda 1 and lambda 2, they are equivalent. Yeah. So once we introduce this equivalent relationship, then we can define the quotient space. Okay, this B is all the binary interactions over this equivalent relationship. And this will consist of all these lambdas, lambda prime, which are equivalent to lambda. Yeah. So once we have defined this equivalent relationship among these among these all the binary interactions based on this permutation group. Yeah. So finally, we have our result, the most important results. And we say that if U is exchangeable, the random variable is exchangeable, and then for any positive integers and for any lambda 1, lambda 2, if these two binary interactions, they are equivalent, then expectation of A lambda 1 will equal the expectation of A lambda 2. Okay. And the converse is also true. Right? So that means if we can show that expectation of A lambda 1 equal expectation of A lambda 2 whenever lambda 1 and lambda 2 are equivalent, so this means that these two random vectors are exchangeable. So this is the if and only if conditions. So this means that the testing of the equivalent of the exchangeability eventually can be converted into the testing of the equality of the expectation among the equivalent class. Yeah. So once we have this result, then the original beauty formula can be simplified. So in this case, this characteristic function of the random vector then can still be written as a linear combination and all these trigonometric functions. But now E of A lambda, we can combine them once this lambda belongs to the same equivalent class. So this will be a common factor, we can move that out. Yeah. So this will be, we call this formula as the brevity, binary expansion approximation of the random variables with exchangeability. Yeah. And then for this exchangeable, it means that for any lambda 1, lambda 2, and if they are equivalent, then expectations are the same. But on the other hand, if we consider independence, the testing of independence which is equivalent to expectation of A lambda all equals 0. So we can see that this condition is much stronger than the exchangeability. So if this equals 0, then automatically expectation of A lambda 1 equals A lambda 2 implies exchangeability, but not the other way. Okay. So because this is our most important results. Yeah. So we have used some knowledge from the abstract algebra, which I learned like 20 years ago when I was a college student. And we never found a way to use this abstract algebra until we work on this project. Yeah. Finally, we can use some terminology from there. Yeah. So all the effort has paid off. Yeah. Yeah. 我们之前有一个 work 我们是做 testing of independence 然后我们在这个基础之上，然后再做这个 testing of the exchangeability. Yeah. So now actually we want to build a connection between the testing of the independence of the testing of the exchangeability. And remember, for the testing of the exchangeability means we want to test the expectation of A lambda are the same among the equivalent class. And then this actually can be converted into the testing of this another problem. So basically, we construct a contrast matrix, okay, representing the equivalent class. By the way, the first step is that we consider all the lambdas, all the binary interactions, then we put them into one single vector, okay? And then for this vector, if this random vector is exchangeable, and then for this vector, some of the entries will be the same. Okay. Then we can construct the contrast matrix, and this matrix, for each row, we only have 1 minus 1 and 1 positive 1, and all the other entries are 0. And the location of minus and 1 will corresponding to an equivalent class. Okay. Then we can test whether expectation of T times AL equals 0. So this is the testing of the exchangeability. Right? And then the testing of the equivalent of the independence. The testing of independence can also be written into this expression. So expectation IAL equals 0. But I here, this is the identity matrix. Okay. So in this sense, actually, we can see that these two problems can be unified under one framework. Okay. And we can also show that we can testing of like complete independence, block independence, or regression dependence, and some other distributional property, like if we want to test where the median being 0, and these are also equivalent to a specific choice of matrix, and we test the expectation of CAL equals 0. So this actually will pave the road, and this will provide a framework for the many testing problems. So if we want to study some other distributional properties. Yeah. Okay. So the next one actually, how much time do I have? 5 minutes. Okay. I'm in a good shape. For data-driven method, actually, yeah. So for fixed P and D, and then we can see actually the data-driven method is closely related to the Newman-Pearson lemma. Yeah. So basically, under the null hypothesis, if the random vector itself is exchangeable, and under null, and we can show that the statistic, the symmetry statistic, which is an estimation of the expectation of A lambda. And this will follow one normal distribution, approximate by one normal distribution. And under the alternative, this can be approximated by another normal distributions. And then we can do some, calculate the Newman-Pearson lemma. Then we can derive our testing method. Yeah. So for these details, then I will skip this. Yeah. So eventually, based on Newman-Pearson lemma, so we introduce a test of statistic, which looks like in this way. So by the way, we apply this tau. This is a soft thresholding. Yeah. Because you can imagine that when we consider all the binary interactions, the number of the binary interactions is huge, 2 to the power of p times d. Yeah. And not all these binary interactions are important. So we want to use some thresholding method to remove some binary interactions to improve the power. Yeah. Okay. And then we just want to show some numerical results. Yeah. And then we consider two different cases or two different types of the exchangeability. And the first one, we consider identical marginal distribution on a non-exchangeable coupler. So that means if we consider original random variable uv from -1 to 1 times -1 to 1, and then this random variable itself is non-exchangeable. But then we apply a marginal transformation to the same marginal transformation. For instance, we can use the normal CDF functions. Yeah. And then this is the one type of the non-exchangeability. And the second one, actually, we assume that we have different marginal transformation. However, if we transform the data to the -1 to 1 times -1 to 1, and after transformation, this random vector is exchangeable. But now we have two different marginal transformation. Okay. So in this case, on the marginal level, they are not exchangeable. Yeah. And this is some simulation results. Then we have proposed method, which we have 3 different versions, M1, M2, and M3. And then we can see that for most of the cases, and we can have a very good power, right? And these are 4 different cases corresponding 4 different parameter settings. But we can see that one of the methods which can potentially work better than us. So this is TXR. Right? So TXR, this method is rank-based test. Okay, rank-based test. So if the rank-based test, we know that this rank-based test is invariant to the marginal transformation. It's invariant to the marginal transformation. So that means, in this case, actually, we have used the same marginal transformation on U and V. So in this case, this will not affect the performance of the rank-based test. So in this case, it works pretty well. But for the second one, okay, we can see the rank-based test works very poorly, because in this case, we have 2 different marginals, and then after the transformation, they will be exchangeable. Okay? But then for the rank-based test, they are not able to detect the non-exchangeability due to the marginal transformation. So from here, we can see that this method has a very low power. And then for our method, it's right here. But in this case, we can see that some other method which works better than us. But if you go back to the previous slides, and these other methods failed completely, failed very badly. Yeah. So this shows that for our method, actually, we have a certain adaptivity. Yeah. So no matter what is original data, the right panel corresponding to the case when we apply the standardization. So basically, we make the data to center around 0 and with variance equals 1. So we just want to remove the moment information on the two different directions. In this case, it turned out that all this method, and including the proposed method, will reject the null hypothesis. So we can see that these two random vectors are not exchangeable on these two directions.
Good morning, everyone. My name is Professor Liu for the kind introduction. And also, I would like to thank Tsinghua University for inviting me to this wonderful place, such a nice place to give a talk. And also, I remember I was invited to Tsinghua University to give a talk like 3 years ago. But at that time, like the department, there's no Department of Statistics, and it is located in a different building right. But and just after 3 years, Tsinghua established its statistics department and moved to a very good building, which we have saw yesterday. So I really appreciate those who make this happen, and I believe this is like a huge contribution to the field of statistics in China and beyond. And now let's focus on my talk. So in today's talk, I will discuss one of my papers, one of my recent papers, which talk about the fine-tuning of large language models. And in particular, we propose a double robust algorithm referred to as, oh, sorry. Referred to as DRPO for alignment. So I guess we are all familiar with large language models, but if we ask those large language models themselves, like what are the large language models? So these are the solutions. So the left picture shows you the solution from ChatGPT, and the right picture shows you the solution from the DeepSeek. So if you look at their answers, you can see like there are something in common. So for instance, all those models, they are of very large scale. They typically have like billions or even trillions of parameters. And I think that's like one of the major difference compared from existing machine learning models. So these LLMs, they are really huge in size. And this picture shows you like the size of different language models. And that's the data up to March 2023, so 2 years ago. And you can see like these models, they vary in size. So we have small models ranging from like 100 million parameters, such as like BERT or GPT-1, to extremely large models with like over 500 billion parameters. And it is also, a rumor also says that the GPT-4 might have like trillions of parameters. And also, as I have mentioned, that's the data up to 2023. So in the future, we might expect it to see like even larger models. And we have definitely entered an era of large language models. So this figure shows you the data for last year, 2024. And if you look at the upper panel, so the upper panel shows you like on average, like every X hours, like those, like how frequent like those new major models were released every X hours. And these new major models refer to models such as like GPT-4, DeepSeek. And you can see that on average, like average 1 day or 2 days, there will be like new major model being released in last year. And if you look at the bottom panel, so these numbers are even more amazing. So it shows you like on average, like the derivative models, which are built based on those major models. So how fast they are being released. And you can see like on average, like every 3 to 5 minutes, 3 to 7 minutes, like those, there will be like a new derivative model appear in being uploaded to Hugging Face. And next, before my talk, I just want to give you some brief background regarding the training of large language models. So training of those large language models typically involve 2 stages. So the first stage is like the pre-training stage. And this is achieved using autoregressive next token prediction. And if you look at the upper panel, so this is a very famous quote from the Avengers Series 4, Iron Man. So essentially, as you can see, it's basically using like the first token to predict the second token. And then use the first 2 tokens, the first 2 words, to predict the third token, so on and so forth. And after pre-training, so those language models, they typically undergoes like another post-training stage. Okay? And in general, there are like two different types of post-training algorithms. And the purpose of post-training is basically to align those large language models with our human values. So yesterday, in yesterday's talk, Professor Song Chunzhu talked a lot about the human values. So that's how we typically align LLMs with our values. Okay? And there are two different post-training algorithms. So the first one is supervised fine-tuning. So the idea is that for each question, for each prompt, we will provide like some high-quality human answers. And then the parameters in the LLMs, they are fine-tuned in a way to align with those human-written solutions. Okay? So that's for supervised fine-tuning. And the second paradigm corresponds to reinforcement learning from human feedback. So the idea is different. So instead of asking humans to directly provide the solutions, so now we ask humans to label the solutions. So here we have like two solutions. Okay? And then among those two solutions, human experts will indicate like which solution is better to give their preference. And then we apply reinforcement learning to fine-tune those LLMs. Right. So we first use pre-training to get the estimated parameter, and then we directly apply like a SGD based on the data, based on this data to the parameter obtained from pre-training to update the model parameters. It's using this data. It's using this data to fine-tune the model. Right. It's like a solution. It's like a solution with multiple tokens. And basically, in today's talk, we will talk about the second paradigm of post-training, which corresponds to reinforcement learning from human feedback. And the idea is basically to apply reinforcement learning for fine-tuning large language models. And before the development of LLMs, so I think reinforcement learning was like one of the most popular research areas in machine learning. And as we probably all know, like last year, the Turing Award was given to Andrew Bartle and Richard Sutton, who are regarded as the fathers of reinforcement learning. And just to give you some background regarding reinforcement learning, so that's also my research area in the past 5 to 6 years. So reinforcement learning is basically concerned with solving those sequential decision-making problems. So we typically assume that there exists an agent that tries to learn and interact with an environment. So at each time point, the agent will observe some features from the environment summarized into a state. And then, based on these features, the agent will choose an action, and afterwards, the environment will provide a reward to the agent. And then the environment will also transit into a next state. Okay? So such a procedure applies sequentially. So at the end, the agent will receive like a sequence of the rewards. Now, the key goal of reinforcement learning is just to try to identify an optimal policy to maximize the cumulative reward that the agent will receive in the long run. And here, I want to point out like two fundamental papers about reinforcement learning from human feedback, or RLHF. So both are new RIPS paper. So the first paper is this 2017 paper, which according to my knowledge, gives like the first introduction to RLHF using deep learning. Okay? And the second paper is this famous instructor GPT paper, which can be viewed as a first successful application of RLHF to fine-tuning LLMs. Now, if you think about reinforcement learning in the context of LLMs, so compared to traditional reinforcement learning problems, so in LLMs, so one of the key difference is that here in the context of LLMs, we do not have like a well-defined reward. So just imagine if you want to get a reward. So this means that for each question, for each response that an LLM generated, we will need to ask the human expert to provide like a real value score to indicate like how good the goodness of this response to solving the question. But as mentioned by this man on the right, so this is extremely difficult for the human expert to provide a numerical score, to provide like a real value score for each of the solution. So to solve this question, what RLHF does instead is that we ask human values to provide the comparisons instead of directly providing the numerical values. So we ask them to compare two answers to indicate like which one is better. Okay? And this is much easier than directly giving the absolute scores. And once we have those comparison data, we estimate the reward based on this comparison data, and then apply reinforcement learning. So that's a key idea of reward learning in RLHF. Now to summarize, for each question, we will have like two or multiple generated responses. And then we ask the human experts to indicate like which response is being preferred. Okay? And next, typically, we will impose like some preference model to model the human response. And one of the most popularly used model is this Brett Terry BT model. So that's a Biometrica paper. And I think this is perhaps like one of the most highly cited paper in statistics that related to LLMs. So I checked the citation yesterday. It has like over 5,000 citations. So if you read this equation, so essentially it's assuming that the probability that one response is being favored is equal to like a sigmoid transformation of the difference in the rewards between the two responses. So if a response has a larger reward, then it has a higher probability of being preferred. Okay? Now, based on this reward model, we can apply like maximum likelihood estimation to directly estimate the reward from the human preference data. So that's a typical reward learning procedure in RLHF. Now, next, I'm going to introduce some existing RLHF algorithms for fine-tuning LLMs. So the first type of baseline algorithm is referred to as those PPO-based algorithm. And that's basically based on the paradigm that I have mentioned earlier. So the idea is that they first apply maximum likelihood estimation to estimate the reward by solving the BT model. And then once you have the reward, you directly apply a reinforcement learning algorithm, which is typically the proximal policy optimization. Yes. That's a good question. So typically, in standard implementation, they assume like there's one model for all the response. But there are also some research that discuss like the human preference might be heterogeneous, and there are some follow-ups along this direction. But in the standard implementation, it's just assuming there's one overall model for the entire data set. Yeah. So that's a first type of baseline algorithm. And the second type of baseline algorithm is referred to as like a DPO-based approach. So here, DPO refers to direct preference optimization. Okay? So if you look at the figure on the left, so this just shows you the procedure that I mentioned. So based on the human preference data, it is like the classical approach. The first type of approach is like a two-step approach. So based on the human preference data, we apply maximum likelihood estimation to estimate the reward. And then based on the estimated reward, we apply reinforcement learning to estimate the optimal policy. And so that's the first type of baseline algorithm that I have just mentioned. Now for this DPO-based approach, it is different. So it's basically like a one-step algorithm. Okay? And if you look at the equation, so the key observation is that they found out that there's like a one-to-one response between the reward function and the optimal policy. And using this one-to-one equivalence, they can express the reward function using the optimal policy. And because of that, there's no need to first estimate the reward function and then to estimate the optimal policy. You can directly, using this expression, to estimate the optimal policy using maximum likelihood estimation in one step. So that's a key idea of this DPO-based approach. Okay? So that's our second baseline algorithm. And also, I want to mention that in this implementation, you also need to specify the reference policy, which corresponds to the policy that generates the solutions, that generates the answers in the preference data. Okay? Right. So here is basically avoiding to estimate the reward. It's basically just to express the reward using the optimal policy, and then. So here it's basically just to apply like a maximum likelihood estimation. So it's avoids like the last step. It avoids the last step. Right. So it means it avoids this step. It avoids this step. It's directly use the maximum likelihood estimation. Okay? So there's no like reinforcement learning step involved. So the reinforcement, they basically use reinforcement learning to obtain this expression, to obtain this closed form expression. And you don't need to apply like a separate reinforcement learning step to learn the optimal policy. So far I have talked about like two types of baseline algorithm. So one corresponds to the PPO-based algorithm, and the other corresponds to the DPO-based algorithm. And here I want to highlight that both type of algorithms, they suffer from certain model misspecification. So firstly, as you can see, both types of algorithms, they rely on the BT model assumption, which can be strong and might be validated in practice. So one assumption entailed under the BT model assumption is like this transitivity assumption. So which means that suppose if we have three answers. Now, if answer 1 is being preferred over answer 2, and answer 2 is being preferred over answer 3, then all under the BT model assumption, it implies that answer 1 must be preferred over answer 3. But there are some previous studies that shows that such a transitivity assumption might be validated. And in that case, the BT model will be validated for sure. And also, even when the BT model assumption is held, so those two baseline algorithms, they can still suffer from certain type of model misspecification. And in particular, those PPO-based algorithms, they can suffer from a misspecification of the reward model because you will need to first estimate the reward and then apply reinforcement to estimate the optimal policy. And if the reward model is misspecified, then the estimated optimal policy can be suboptimal. And this is a phenomenon referred to as reward hacking in the literature. Okay? And for the DPO-based algorithm, so although it doesn't involve the estimation of the reward, but the resulting algorithms can suffer from the misspecification of the reference policy. And this is because I just want to remind you, so in this formulation, the reward model depends on the reference policy, okay, which generates the responses in the preference data. And because of that, for the second type of algorithm, for those DPO-based algorithm, although it doesn't suffer from the specification of the misspecification of the reward, but it suffers from the misspecification of the reference policy. And there are like another type of baseline algorithm, this preference-based approach. So for instance, there are some recent works that formulates this fine-tuning problem using like a two-player zero-sum game and focus on like identifying an optimal policy by solving this minimax formulation. And there are also some recent proposals that propose those like more general preference model beyond the BT models. And there's also like this identity preference optimization algorithm. Okay, so in summary, these models, they also suffer from they can also suffer from the misspecification of the preference model. So in summary, all these three types of baseline algorithms, they suffer from certain model misspecification. So as I have mentioned earlier, so the first two type of algorithms, DPO and PPO based, they rely on the BT model assumption to hold. And when it is violated, then the routing algorithm is not guaranteed. And even if the BT model assumption holds, then the PPO algorithm can still suffer from the misspecification of the reward. And the DPO-based algorithm can suffer from the misspecification of the reference policy. And our proposed algorithm is referred to as DRPO. So it's basically like a double robust algorithm. And as I show you in the table, it is more robust to the misspecification of the models. Okay, so just to give you a summary of our contributions. So our main contribution is to basically to apply double robust algorithms for those LLM fine tuning, and we also derived some series regarding like double robustness property of our estimator and the statistical and like semi-parametric efficiency of our proposed estimator, and we also conduct numerical experiments to demonstrate the advantages of our proposed algorithm. So the idea of our proposal is very simple. So the main idea is basically to use like those double robust methods that are classically developed in the missing data and the causal inference literature for LLM fine-tuning. And those double robust methods, they just to give you some background for those of you that are not familiar with those double robust methods. So let's consider the problem of the estimation of the average treatment effect in causal inference. So suppose we are interested in estimating like the difference in patient's outcome between two drugs. Suppose we have two drugs and we are interested to know like what are the difference of having those two different drugs. And then those double robust methods, they typically estimate two models. Okay? So the first model corresponds to like a propensity score model, which indicates like the probability for each patient to having like a particular. And that's basically similar to the reference policy that generates the solutions in the preference data in LLM. And the second model is like an outcome regression model, which models the patient's outcome for given the treatment. And that's basically very similar to the reward model that I have just mentioned in LLMs. Now, for those double robust methods, they estimate both models to construct the resulting average treatment effect estimator. And it turns out that the consistency of the resulting estimator only requires like one of the models to be correctly specified. And when both models they are correct, and it is known that the resulting estimator it becomes semi-parametrically efficient. So it is the most efficient estimator among like a large class of regular and asymptotic linear estimators. And due to those nice theoretical properties, so those double robust methods, they were later like widely studied and extended in the literature. And here I listed like several problems where those methods were being extended. So basically, the main idea of our proposal can be summarized using this figure. So basically, if you look at this figure, so for each question, so you can see there's like a machine, there's like an LLM that generates like two responses. Okay? And then for those two responses, we have like a human expert to provide the labels to indicate like which response is better. Now, for our proposed model, for our proposed algorithm, it requires to specify two models. It requires to specify the two models. So one corresponds to the reference policy, and the other corresponds to the preference model. Okay? And both models, they can either be correctly specified or they can be misspecified. So here, so reference policy is the policy that generates the preference, that generates the responses in the preference data. Let me see. So here it's basically the policy that generates like these responses given the prompt. Right. It's similar to like the propensity score. So if you look at this figure, so basically it refers to the policy that generates these responses. Okay? So for each query, we first generate these responses, and then we ask the human experts to give the labels. And the reference policy describes like the procedure for generating these responses. And you can see that so for either the reference policy or the preference model, the models can be correctly specified or they can be misspecified. So this gives like a total of 4 different combinations. Okay? So whether one model is correctly specified or misspecified. And among those 4 different combinations, so 3 of them will gives the optimal solution. Okay? And only when both models they are misspecified, then it will give the suboptimal policy. Right. So firstly, that's one of the standard procedure. So for each question, so firstly, you either ask like the model or you can ask the humans to generate the 2 responses, and then humans they will provide the labels. Okay? But this is just an illustration. Any other questions at this point? How many time do I have? So I guess I will basically skip this slide, but this slide describes the detailed procedure, how we apply those double robust methods for LLM fine-tuning. So we basically develop a double robust objective function, and then to optimize this objective function for LLM fine-tuning. And we conduct some numerical experiments, so I will just skip this slide. And finally, this is like a summary of our theoretical results. So we show the double robustness property of our estimator, and we also show like the semi-parametric efficiency. And if you look at the last bullet point, so we also derived like the sub-optimality gap, which corresponds to the difference between the reward of the optimal policy and that under our estimated optimal policy. So you can see that for 2 baseline algorithms, such as like PPO or DPO-based algorithm, so for these algorithms, the estimation error of the reward and the reference policy affect the suboptimality gap in first order. Okay? But if you look at our suboptimality gap, so these estimation errors, they appear as a product. So they affect the suboptimality gap in the second order. Okay? And that's basically due to the use of double robustness property, which guarantees that the resulting estimator, it is not highly sensitive to the estimation of either of the errors in either of the models. And due to time limit, I guess I will just skip the details. But if you are interested, you can find the papers on my personal website. Thank you very much for coming to my talk. Thank you. So for instance, what OpenAI did is that they recruit like lots of interns, and then to ask those interns to provide. Right. So here we are basically like using some common benchmark data set to run our experiments. But if you really want to build a large language model, then right. Right, but if you want to build a large language model yourself, then you probably want to like recruit someone in order to provide the labels.
行，由于时间关系，我们有问题可以之后再和石老师讨论。 Our next speaker is Pengkun Yang from Tsinghua University, and his research interests include statistical inference, learning optimization, and systems. Today he will talk about fast and multiple fish rates for nearest neighbor classifiers. Let's welcome.
Thank you. Okay, thank you all for coming to the conference, to our summit. I should have been in France attending the code the conference. So I was asked by Ke to stay here and joining our summit. So it turns out that so I will present our work that was will be shown in the code conference in this year. Our work is on the fast and multi-phase rate for nearest neighbor classifiers, and this is based on joint work with Jinzhao Zhang from Tsinghua IS. And to begin with, in this conference, we discussed a lot about the connection between machine learning and statistics. In particular, in this talk, we want to discuss the connection to non-parametric statistics. And in my opinion, from a theoretical perspective, the machine learning is very similar to non-parametric statistics. The task is very similar. We have regression or classification. And for the reinforcement learning problems, we actually use some sequential models. And the machine learning models, in particular, the current the neural nets or even transformers, they have super power. They can approximate any functions, just like in the last talk in Professor Yu Xingchen's, the transformers can approximate many statistical procedures. And they can solve some problems. So those models, although strictly speaking, they have the neural nets have certain parameters, but there are too many. So I think they should be viewed as non-parametric models. But on the other hand, practically the machine learning is very different from what we see from the classical non-parametric statistics, especially in those high-dimensional problems. The large models are very effective for those high-dimensional problems. So in my work, we want to understand where is the gap. I also discuss many young scholars, and we work on theory, but we can see a huge gap between the current theoretical progress and the practical performance we see in many large models. So first, we review some classical tools to study the theory of those large models. Here is the framework. We have untraining data, and we use the training data to train a predictor I've had, and we test this predictor to get a risk R. And there is one set of approach that working some hypothesis class F, and this may be viewed as a parametric method. If F is a linear function, it's a parametric family, or if some F with certain complexity measures, they also have some parametric approximation. And the risk over this family is defined as RF star, and there is a line of work studying the empirical risk minimization. And for this approach, they can prove the rate of convergence, which is the risk of F star subtract. Where is the control? Yeah. Okay. The F star converges at a square root of VC dimension of the function class F divided by the sample size, the training data size. The pros of this approach is that this theory, the rate of convergence is distribution free, and they can achieve fast rate if the VC dimension of the function class is simple, such as the linear function is just a dimension. But the cons is we have a dilemma to choose the hypothesis class F. If we choose a simple class, then the power could be, the model capacity is small. We suffer from a large RF star. If we choose super sophisticated models like neural nets or transformers, the VC dimension of those or some random forest, the VC dimension could be super huge. So the rate of convergence can be also pessimistic in this case. And there is another line of work working with universal approximators. And in this line of work, the f hat will convert to the some notion of f hat n will convert to some notion of f star. The f star can be defined via the regression function, which is if we know the underlying model pxy, then we know what the best f star is, but that requires knowledge of p. And in this case, the base error is the minimum risk over all the possible functions. And we also prove in the past that people also prove many rate of convergences for smooth functions and for functions for the pxy with certain margin conditions. But those rate of convergence can be achieved by many methods, including the classical paper using kernels or local polynomials, and in the recent papers by nearest neighbor or neural nets or random forest. But in those work, the downside of the result, the pros of this approach is that the RB star is often very small. If the neighbor has no noise, then RB star will be 0. And the downside of this approach is that here we have a factor of d in the denominator, which means that if we want to achieve a small risk, like this number is less than 0.1, then the sample size needs to grow like e to the d. It's also very pessimistic in practice. In practice, it's very rare, since the problem dimension is very high. It's very rare to have such a huge sample size. But in this talk, we run a simple numerical study. We run the nearest neighbor methods, and we use the simple training data set, the MNIST handwritten digits. The input dimension is over 700. And it turns out we found this type of curve. The x-axis is the sample size, the y-axis is misclassification rate. In fact, this method is also tested in Yan Quinn's classical paper in 1998, but in his paper, he only tested the last point. He input the entire 60,000 training data input, and he tested the model with the 10,000 test data. And in his paper, he reported that the test error is less than 1%. In our paper, in our numerical study, we input the training data in small batches. We input the first 100, 1,000 until the entire training data. Then to find the rate of convergence, we just need to, since this is a log-log plot, we need to find the slope in the plot in the log-log plot. And we found that the slope is nearly 1/2. If we increase the sample size to about 4-fold, then the test error will decrease by nearly 1/2. So the rate of convergence is nearly into the 1/2. Is nearly parametric rate. But to my knowledge, there is no theory showing that the parametric rate can be achieved with such a type of local methods. We also look into the theory of nearest neighbor classifications. The method is very simple, just the majority vote among the k nearest neighbors. And the large sample limit is proved in many, is nearly 50 years ago. And the rate of convergence is a more recent endeavor. They prove that the similar rate of convergence means that on the beta holder smooth condition and on the extra alpha margin conditions, the rate is similar to the classical non-parametric rates. And there is some other studies showing that if they can improve the d to the intrinsic dimension d star, which is can be defined as the doubling dimension of the input features. But this rate is still too slow unless the D star is 1 or 2. Since here is 2 plus D star, so to match the n to the 1/2 rate, the D star should be 0. But even if the MNIST is a simple data set, but the numerical results showing that the intrinsic dimension should be of order 10s. But that's far from the rate we see from our study. So we see a big gap between the theory and the practice. So we want to, in this work, we want to provide one answer that why there is such a huge gap. We also run a different study. We change from MNIST to a similar data set. It's called fashion MNIST. Now we see a two-phase of the scaling of the arrow. In the first phase, the decay of arrow is nearly the same as the MNIST, and in the second phase, the rate will be much slower. The slope is much smaller. So from our study, we found that it depends on how complex the input data is. For instance, in the fashion MNIST, the pullover can be very similar to the shirts, and the sneaker can be similar to ankle boots. So these are the hard instances which will contribute to the second phase. But it's for a model, it's very easy to distinguish shoes to shirts. So those parts we can narrow down the 10 classes to about 3 or 4 classes. But in the second phase, we need to tell it's a sneaker or it's an ankle boot. So the philosophy is very simple from our study. We should answer some simple questions first. Then we should identify where are tough ones. So from this picture, question is, what's the rate on convergence? The classical notion of rate convergence is local speed approaching some limit, which means that as n diverges, the slope of the last phase. So to follow the classical notion of for the rate of convergence, we should find the slope in the second phase, and which is much slower than the n to the 1/2 rate. But the fast learning in the first phase is not captured by our notion of rate of convergence. In fact, with only about 200 training data, the model can classify about 70% of all the tests. We have 10,000. It can classify about 7,000, which to me is a pretty good performance with only this small sample size. The 10,000 tests, we can classify about 7,000. Actually, although our numerical is only on the nearest neighbors, but similar trends can be also seen on transformers. Like this is a paper by studying the transformers on the topic of scaling loss. And we can see also several phases. In the first phase, the loss will decay fast, but there are also second slow phases, whereas the decay of arrow is much slower than the first phase. Those are real data. We don't have a model for them, but it's not hard to recover the curves in very simple simulations. Here is just a d-dimensional hypercube, and half of them are positive, the other half are negative, and we draw some training data, and we train a nearest neighbor, and we test the model on a test set. And the test error can be seen in this curve, and the slope is also nearly 1/2. And in the second numerical study, we slightly rotate the decision boundary to then we can see two phases. In the first phase, the decay of arrow is almost the same as the first part, but and the arrow will decrease from 1/2 to nearly a quarter. And from this point, the decay of arrow will be much slower. So we see also can see a two phases in the decay of error. And from our study, from our understanding, we see that those are the simple points which can be learned with very small number of training data. But the point near the corner will be very hard, since the corner here, if we use we have a small training data, we need to use a large radius, since in high dimension, we need a large radius to see a sufficient number of training data inside the ball. And inside this ball, this point in this sense is closer to the wrong side than the right side. We need to huge sample size to reduce the radius such that the neighborhood is dominated by the red points. So we need to characterize the set of hard points. And there's a notion, similar, related notion in classification is called Sipakov's margin condition. It's used for the theory of classification tasks. And the intuition is that if the point is close to the decision boundary, it will be a hard point. But here we found that this Sipakov's margin condition can only capture the hardness in the local sense. We need to go to a small ball, since this is how smooth this regression function is. And in our study, the key ingredient is a microscopic viewpoint of the machine learning method. We decompose in our study. We want to understand what is the En, which is the R of F star subtract of the Bayesian risk R B star. And this can be decomposed as a weighted average of the error, where the F hat star is not equal to F star. F hat X is not equal to F star X. And if we have N test points, then we can, this En is close to the sample average of all the misclassified points in the test set. And in fact, those set of 0, 1 values is just a set of Bernoulli random variables, where the randomness is over the training data. And here we can define the microstate at the point X, which is an unobserved mean of those Bernoulli random variables. It's the probability of F hat X is not equal to F star X. We define it as a macrostate of this k-nearest neighbor at point X. And here N is the training data, the number of training data. And then we want to quantify the microstate. But our intuition is from the map estimator, but the map estimator requires knowledge of the joint density of PXY. And it's also very hard to find out what's the pointwise density given capital X is at a small x. Our idea is to go to a smooth version of the map estimator. We replace the point X to a ball of centered at X with radius R. And for clarity, let's consider the binary classification. The relative singular strength can be defined as the ratio between the P of Y is correct given in the ball of radius R over the P of Y being incorrect given the ball of radius R. And we only need to consider typical radius where the probability mass is about rho, which is K over N. So with N training data, we have a K test point, a K training point inside the radius. And we do a rescaling, then we found that the first lemma in our work is that the microstate is upper bounded by this number, is some C times the number of training data, and here is the state. Here is the tau rho X, and the wedge. Here is the typo, it should be rho. And then we can go from our microscopic analysis viewpoint to understand where is the En, which is the weighted average of those small e of n given x. and we define a set of nested subspaces, and we can propose a majorizing function per side to capture the complexity of the input distribution P. Okay, now let's go to some of our main results. If we use a k nearest neighbor, and let's rho be k over n, and if P satisfies some complexity measure, then we can upper bound it by the excess risk to be the sum of 3 terms. The last term is a large deviation result, which means that k nearest neighbor is fall outside the typical radius. And the first term is the total mass of the hard points, and the second term is the fast scaling of the simple points. And if, in addition, the alpha margin condition is satisfied, then the second term will decay at a faster rate. And then we can partition the input space into different hardness regions, and we can achieve a fast rate in the simple points, and we suffer from a slow rate in the hard points. And this is a pictorial where the final radar convergence is achieved at the junction of those 2 curves. And first, we can, from our general result, we can recover the classical non-parametric rates. Then I think I will skip this part. And we can derive many results in the classical study of non-parametric statistics and k nearest neighbors. The rate is similar, is the minimax rate achieved by minimizing over the rho. And we can also derive some new results. And let's go back to our study in our syntactic studies. We consider a logic model with normal design, and then we can show that the radar convergence. We can also derive the psi function, and from this psi function, we derive that the excess risk is d over n rho to the power of 1 plus alpha over 2. And for this model in particular, the alpha is 1, so we find that the final excess risk, the radar convergence is d over n, which is the same as the linear functions, although this is a non-parametric method. We don't use the prior knowledge of the linear structure. And we also have other, although this result is only, this page is only talk about logic model. Actually, the result can be also applied to other models like probability or Gaussian mixtures for classification. And we can also achieve the similar rate of convergence. And finally, go to the 2 phases, the multi-phase rate. That's where the simple point will converge faster, the macro state will decay faster with n, and the point near the corner will decay much slower. The macro state is have smaller parameters, and combining those 2, we can derive the 2 phases of the psi function, and can give the 2 phases rate of in the decay of arrow. And the conclusion is that our focus is on this plot. We show that even for non-parametric methods, it can achieve faster rate of convergence for certain input distributions, such as the logic model. And in general, we can have multi-phases for the decay of arrow. And there are many future directions. We actually sum of not a future direction as a starting point of our study. We start from some understanding the large model and neural networks, but with no avail. And the nearest neighbors are more amenable to theoretical analysis. And we also need to provide some procedures to identify the end of the fast phase and where are the hard points. And those microscopic analysis, we think is also possible, can also possibly provide a theory for other phenomena, such as the double descent of and the grokking phenomena. Those phenomena have several phases. The grokking has, at the beginning, the test can be flat, but then it will jump to a high, the good performance. And this is the references. The code is just in these days from June 13 to July 4th. Yeah, thank you. I'm happy to take questions.
由于时间关系，如果大家有问题，可以之后跟彭坤讨论一下。Our last speaker is Simon Du from University of Washington, and his research includes machine learning, such as deep learning, representation learning, and reinforcement learning. And he will talk about global convergence of gradient EM for over-parameterized Gaussian mixtures. Let's welcome.
Hello everyone, it's my great pleasure to give a talk on our recent work. I mostly do more modern topics like large language models, deep learning theory, reinforcement learning. But today, since this is like a statistics conference, so I'm going to talk about something kind of very classical on EM algorithm and Gaussian mixtures. So this is a joint work with my postdoc, Mo Zhou, my PhD student, Wei Hang Xu, and my colleague, Mariam Faisal. So Gaussian mixture, everyone knows it. It's a classical generative model widely used in multimodal data modeling in statistical machine learning. And then arguably the most popular algorithms to learn the parameters in Gaussian mixture model are, say, EM algorithm, or there's also a variant using a gradient descent based like gradient EM. So in this work, we study the over-parameterized regime, where basically we have more parameters than what is necessary in the, say, ground truth Gaussian mixture model. This is arguably more important in modern machine learning regime, where in modern machine learning models we have a lot of parameters. Sometimes like it's the same scale as the number of data. All right, so this is a setup. So we have some ground truths, say M component, Gaussian mixtures. So here pi I star, they are just the Gaussian like weight for each mixture. And then phi mu I star x is the standard Gaussian density function with the mean mu and identity covariance. Okay, that's a very standard classical Gaussian mixture model. And we call P star the ground truth Gaussian mixture. So our learning model, the model we actually fit, is this Px. So here we have n mixture, yeah. N, in our case, I'll be more specific. N is bigger than M. So that's why we call it over-parameterized. So in our model, we don't, when we fit it, we just use N. So if we can choose a, like, kind of large N so that it's sufficient to fit M. Yeah, so, yeah. We're now studying the model selection problems. Here, we mostly focus on the optimization aspect of EM algorithm. Yeah, we'll see it more clear in the later slides. Okay, so our model, our fitting model, we have n mixtures. Pi I is the weight for each mixture, and then our fitting parameter mu I is mean for each mixture. Okay, and then this like for a mixture model with the sum of pi I and pi star, their sum is 1. And our goal is just to recover the ground truth P star with our model. So here, if n is bigger than m, then at least this model, our model, is sufficient to represent the ground truth model. Okay, so here's a brief review of gradient EM. Okay, so for the E step, we basically compute the membership weights for each data. So here, our current model, let's say, is phi I for the phi mu I. That's for the TC iteration. We evaluate its probability, and then for this data X, we can compute the probability that this X belongs to the I's mixture. So that's a standard E step. And then for the M step, we have this Q function, and then we just apply this kind of gradient descent for this Q function, which is basically the log likelihood function. Okay. All right. So here's a review of prior work on this problem. So the analysis of EM, or the algorithm, of course, like several decades. And then the first analysis I'm aware of is by Jeff Wu back in 1983, like 40 years ago. But they only show that convert to some stationary point instead of converging to recovering the global ground truth of the Gaussian mixture. And then there's a later work by, I think, by McJordan's group in 1990s. Again, they only show some convergence to stationary point. So the formal guarantees for EM for Gaussian mixture starts with around 2016, 2017. The first line is by Tsinghua, Martin Wainwright, and Bin Yu. They show local convergence of EM algorithm for Gaussian mixtures, where the ground truth has 2 Gaussians, and their fitting model has 2 Gaussians as well. They show a local convergence, and then basically based on some convex optimization argument. And then around the same year, there are several works that prove a global convergence. So global convergence or global landscape is no longer a convex landscape. It is a non-convex one. But for m equals to n equals to 2, the case, like 2 Gaussian case, you can actually show a global convergence. And then later, people extend the first line of work to arbitrary number of mixtures, but they only provide a guarantee for the local convergence. Basically, you need to start with your model that is already very close to the ground truth mixture of Gaussians, and then you start applying EM or gradient EM, you can recover the ground truth. Okay? And then later, people have studied this kind of what we call over-parameterization or misspecification cases, where n does not necessarily equal to m. Okay? You can see there are several works, m equals to 1, n equals to 2, m equals to 2, 3, n equals to 2. And then we have recent work, n is arbitrary, m equals to 1. Like those are kind of over-parameterized case. But those are, the m, the ground truth, is very small, like 1 or 2. And then this work in 2016 by Qijin, Yuchen Zhang, Siva, Martin Wainwright, McJordan, they show that they construct an example where they show that if the ground truth Gaussian mixture has 3 components and they are well separated, okay, so it's a very nice case. But if you only have 3 Gaussian mixers and you apply, say, EM algorithm with randomization, you will stuck at some local minima. So because it's a non-convex landscape, if you apply randomization EM, and at least for that case, you will stuck at some local minima. So EM will fail for that case. So this is our work. We show the power of over-parameterization. Let's say m is arbitrary, the ground truth number of mixtures is arbitrary. But if our fitting model number of mixtures is m log m, so m log m is basically from the coupon collector problem. Like you can cover, if you do randomization, you can cover every kind of, you have, when you do randomization, you have one learning mean for each ground truth mean that is close. That's why there's a m log m term there. And then we can establish a global convergence from randomization that recover the ground truth or recover the ground truth density function. Okay, so that's our results. We use gradient EM. Yeah. Right. I will talk about initial point, but basically it's randomization. But we have some other assumption about separation and something like that. So overpolarization, there's a folklore back in 20s from Sanjoy Das Gupta's group where they say like overpolarization improves the optimization landscape and enables like EM or gradient EM convert globally to ground truth gradient Gaussian mixture models. And here basically our recent work gave a formal proof for this folklore, at least under some condition of the ground truth Gaussian mixtures. Okay. So here's a more formal setup of the algorithm we analyze. It's a gradient EM. The ground truth is like it's like that. Our model is like pi I phi mu I x. So first observation is that you apply gradient EM, then it's basically equivalent to applying gradient descent on the KL divergence between the ground truth Gaussian and your fitting ground truth Gaussian mixture and your model. And here's our setup. So we do randomization from the ground truth. Basically, it's equivalent to selecting, say, n points from your samples. And then we initialize the weight for each our model just by 1 over n, because we have n mixtures. To update the weight, we just do, let's say we just solve it for the loss function, fixing mu. And then it's a convex problem, so we can solve it efficiently. And to update mu, we apply gradient descent on this loss function. Okay, hope this is clear. All right, so here's our technical assumptions. These are, I would say, not necessary information theoretically, but to analyze this random initialized gradient EM, this is what we need for now. Of course, there's a open problem how to relax those problems. Okay, so first, on the first line, there's the largest ground truth weight over the smallest ground truth weight. We assume it's O1. This is only a technique, like for the simplicity of this talk, but as long as bounded, then our theory carries through. So these three assumptions are what we really need in our current proof. The open problem is how to relax them. So first of all, we assume those means are linearly independent. Because, yeah, we assume variance are identity, like the kind of simplest Gaussian mixtures. So we assume the means they are linearly independent. In our proof, we connect our like gradient EM to tensor methods. Where there you need some like identifiability property, which is kind of equivalent to mu I star are linearly independent. And second one is like a regularity condition. We assume the mu i's are upper and lower bounded. So our bound depends on this upper and lower bound. And third one is a separation. So this is a kind of standard assumption in learning of Gaussian mixtures. We assume it's fairly large. It's omega sort of d. Information theoretically, at least according to folklore, it should be square root of log of number of mixtures. So there's still a big gap between what we need and what information is theoretically needed. And if you have square root of log m, you can apply sum of square, those kind of algorithm to recover the ground truth mixture of Gaussian. But for the EM, ours is the first work, and these are the assumption we need. If you are to justify these assumptions, if you say if those means are sampled from some prior distribution like this, if the variance is large enough, then you can guarantee these assumptions. Just some justification of these assumptions are not too strong. With high probability. If it's high probability, these are, yeah. Yeah, so this is our formal theorem. Under those assumptions, if the fitting models number of mixtures is m log m, and we use a small enough step size, then gradient EM convert with high probability to the ground truth at the polynomial rate. So here we did not optimize the rate. It's like polynomial in all these parameters. Yeah, another open problem is how to optimize the convergence rate. But this is the first global convergence result for recovering ground truth Gaussian mixtures for number of mixtures bigger than 2. We also have a sample complexity analysis, polynomial in all these parameters. Again, it's not tight, but it's still. Yeah. For m log m, just by coupon collector problem, right? So you do have a high probability that you have. Maybe let me show you a plot. I mean, I'll show you like why m log m is enough in the thing like n is a ground truth number of components. Yes. Yeah. Sure. Yeah. So we have n is m log m. Like okay, it's the order of m log m. So if I have 6 or something. Oh, so it's a relative distance that matters more. So as long as you have, maybe I will show the plot now. So let's say you have 3 components here, like we suggested. It can be in high dimension, whatever. Let's say we have 4 initialization points. So here we may have 2 that is close to this ground truth, one here. So in this case, this is a failure case because for this point, there's only 1 point close to this, but this point, maybe there's nothing or no initialization point close to this. But if you have m in the order of m log m, okay, then for every ground truth, you have 1 point that is closest to that point compared to other. It's relative. Okay. Okay. No. Okay. It's not about. So by close, I mean relative distance. So as long for this point, compared to your, so for this point, I mean compared to other ground truth means, this point is closer to this point. Then that's what we mean by there's at least 1 point cover this ground truth. It's not like a absolute distance, relative distance for each initialization point to the ground truth point. So it's only a relative distance. We only for the algorithm to succeed, it will convert to the closest mean. So as long as there's 1 ground truth, maybe let me show you. So for example, these red dots, these are the ground truths. As long as for every red dot, there's 1 initialization such that this particular red dot, that initialization is closer to this particular red dot, then you can succeed. It doesn't need to, yeah. I mean, that for relative distance, then that is a common collector problem. It has nothing to do with dimension then. You only consider the relative distance because you only consider whether I'm close to this ground truth or that ground truth Gaussian, right? We initialize this from the ground truth Gaussian, right? We pick, so with m. We also have this large separation, so that's kind of help the help this coupon collector. So. Okay, so these are the sum. So first of all, because the max weight over mean weight is like theta 1, So you still have non-trivial point in for that far away ground truth, right? And secondly, you have a large separation. Then you, for that far away ground truth Gaussian, with random transition, you still have non-trivial weight that is, or non-trivial chance that is close to that far away Gaussian. For the first assumption and this assumption. Initialization 跟这是有关系的，因为它这个是对OK。对，但会有它有时候会离这个近，有时候离这个近。对。当你有，所以说你光 truth 有这些 assumption 的时候，它对的对的，但你有这个 assumption 以及最上面那个 assumption， 它 approximate。不，这是我们所有这个 assumption 我们都需要的。一个是 large separation， 一个是它的光 truth weight 都是theta 1， 这个比例是 theta 1的。对，所以它这个 close enough to 这个 equal probability。对。Any other questions? Okay. Yeah. So let me also mention that even for the same assumptions with some initialization condition, then if you do not use overparameterization like m equals to n, then with high probability it will fail convert to a local minimum. This is by prior work by Michael Jordan and Martin Wainwright's group. So they construct an example. So here we do show that there's a strict benefit of being overparameterization, kind of coupon collector, such that you can convert globally to the recovered ground truth. Okay, so here's our why just random transition help. Basically, it's kind of coupon collector or close. So you can avoid this one fits many local minimum conditions. So in their example, let's say this is a failure case where you may initialize this case, and this one is kind of one fits many. So it will stuck at some local minimum. Okay. Yeah. So, but for our case, if you do overparameterization, then basically for every ground truth Gaussian, you have one learning Gaussian that's close to it and will converge to it. I'll skip. So here, those are the results, and I'll just mention some of the key challenges in our proof. So first of all, we have some partition. One challenge is that actually the mu I, the mean, may not converge to any ground truth component. You can verify that even in the simulation. Because its corresponding weight, pi I, can be 0. So actually, the final result will be something like this. Either mu I converts to one of the ground truth mu I star, or its ground truth pi, or the corresponding pi I, the weight, converts to 0. And then another challenge, like some cross term, like you need to handle the probability of you are close to one ground truth, but you also have probability that from the other ground truth Gaussian. Okay. Yeah, so the high level idea is to establish this gradient lower bound or the PL condition if you're familiar with non-convex optimization. you need to search for some decent direction about the laws, and if you can establish that the gradient norm is bigger than some order of the loss, then you can have a global convergence. The key idea is how to construct this descent direction. Descent direction at a high level is just for each mean, you consider the distance between this mean and its closest ground truth mean. So that's this term. So basically, you can establish like gradient lower bound like this. And we have two phases. One is a global phase where we can convert to some epsilon 0 in the order of, this is a global phase in the order of exponential of the separation, and there's a local convergence phase where you can need to separate, do some detailed analysis where you need to ignore some mixture whose, for example, this one, whose corresponding pi I, the weight, is already very, very small. The key idea in our proof, actually we leverage a lot of, or several new ideas, not in the standard EM analysis. It's borrowed from more recent non-convex analysis from neural networks. So first of all, we use Hermite polynomial to connect the loss with a parameter arrow in parameter. For example, this is what we call linear term. It's like linear in this mu i's. And this is what we call the second moment term. It's mu I minus mu, like ground truth norm square. And then you have the weight. To connect the loss with this kind of mass of like arrow terms in mass of moments or parameter arrow, we use Hermite polynomial to establish connection. And then to kind of reduce this analysis of EM to tensor decomposition. And then in the analysis, we want to deal with establish some lower bound for KL divergence, where we use this kind of a homotopy method to do that. Okay, so in summary, we give the first global convergence for this overparameterized gradient EM. Of course, we have several conditions which are open problem to resolve. But I think our technical tools are quite general to further study. We use the Hermite polynomials to establish connection between EM analysis and mass of moments or tensor methods. And we use some test function idea to establish connection as well. And these are the open problems. Can we improve the convergence rate, either in optimization or sample complexity? We improve those conditions like separation. And we only analyze the gradient EM. It's an open problem how to analyze a standard EM algorithm. And thank you. I think that's all I have.
Good afternoon. Welcome to this session. The next speaker is Weijie Su. Let me introduce her. Weijie Su is an associate professor in the Watson Statistics and Data Science department, and by courtesy in the Department of Computer and Information Science at the University of Pennsylvania. He is a co-director of the Penn's research in machine learning. Prior to joining Penn, he received his PhD from Stanford University in 2016, and a bachelor's degree from Peking University in 2011. His research interests span privacy-preserving data analysis, optimization, high-dimensional analysis, and deep learning theory. He received many awards, such as the NSF Career Award in 2019 and Alfred Silent Research Fellowship in 2022, and same Early Career Prize in Data Science and Ames Peter Gavin Hall Prize in 2022. Let's welcome Mr. Weijie Su. Thank you.
Thank you, Professor Fang, for the introduction. Yeah, thank you very much for inviting me to celebrate the 1-year anniversary of the establishment of the Tsinghua Statistics and the Data Science Department. It's really a great privilege for me. So in this talk, I will discuss some of my recent research about large language models. And in particular, we will address this question: do LLMs really need statistical foundations? Okay. So this is the beginning of the story. So imagine that there's an octopus living under the seabed, which has access to the fiber. Okay, and the octopus can listen to people's conversations. Okay, how are you? And good, thank you. So imagine that if you let the octopus listen our conversations for 1 million of years, can the octopus finally understand human language, human knowledge? Okay, so this is the next one prediction, essentially, and which was suggested by Ilya Sutskever in like 7 years ago. 7 years ago, very few, most people doubt. Okay, most people thought this is unlikely to lead to any kind of intelligence. But now we realize that this is not the case. Okay, now we have OpenAI, Gemini, and DeepSeek, okay, competing each other, and we are using these language models in our daily life. Okay, and now what's the most popular programming language? It's going to be English or maybe Chinese. And this makes Turing test a little bit outdated. And so this is an article by my Wharton colleague showing that actually there is a strong impact on the labor market from these LLMs. So this is arms race, and I needed to constantly update the numbers that makes the model, because the model becomes larger and larger every day. Okay, and like GPT has this number, but now DeepSeek has this larger 600 100 billion parameters. I think Llama 4 has larger model size. Okay, and as a statistician, when I first saw language models coming out like 2.5 years ago, I was wondering what we statisticians should do for AI. Okay, and so this is some comics we often like make fun of computer scientists. Yeah, I think it's not a secret, right? And so because this is basically saying that machine learning, or maybe broadly artificial intelligence, is basically statistics discussed. Okay, this statistic with a little bit of decoration, okay? Which is good. Hopefully this is the reality. But meanwhile, many of us actually a little bit pessimistic. Looks like AI could replace us in some day, right? Because AI is so powerful.
And this is not only among statisticians, it's among a broader communities in science, and including chemistry and physics, because Nobel Prize went to physics and chemistry last year, right? Actually, this is only becomes the beginning. And there will be more Nobel Prizes go to AI in the next few years. So the impact from AI on statistics is very clear, right? And because we know that ChatGPT can do a little bit data analysis for us, and the capabilities is increasing every day. In particular, it's very good at data visualization. In the past, I feel a little bit difficult to memorize the ggplot command to make a beautiful plots. But now we can easily ask using language, using human understandable language to let language model to plot beautiful plots for us. But in this talk, we want to ask this, in the other side, we want to ask, how can statistics make AI a little bit better, okay? So this is our talk. So we want, before addressing this question, and we first need to ask a philosophical question. Do statistics really need, do AI really need statistics? So first, let's look at the bit lesson by Richard Sutton, who just got Turing Award early this year. So he has a famous article, and in this article, he said that statistics and competition came to dominate the field. Instead, human hard-coded knowledge actually is not the way to dominate AI. It's not the way to have AI which could lead to enduring effect. It's going to be statistics and competition, because statistics and competition is the way to directly let data speak for themselves. Okay? And Yan LeCun is another Turing Award laureate. He said that LLMs are autoregressive. Then by definition, is statistical, right? By definition. But of course, we want to be a little bit narrow because the statistics in the language of Richard Sutton and Yan LeCun is a little bit broad. Okay, now let's look at the statistical in the sense of Leo Bremen and Brad Ephron. Okay, the data modeling culture in his famous two culture papers. Still, my argument is that AI needs statistics. Why? Because language models basically is the first time where we can process text as easy as numbers. And moreover, by design, it's next term prediction, right? Including diffusion models. It's very stochastic. So this essentially makes language models or diffusion models basically a statistical model. So there's a famous article by Ted Chang 2 years ago. The title is very touching. He said, ChatGPT is basically a blurry JPEG of the web, a compression of all the data we have on the internet. And moreover, transformer is a black box, right? And the gap between theory and the practice to understanding the underlying mechanism of AI transformer is becoming larger and larger. In this case, actually, AI research is more like biology instead of physics. In biology, we need lots of statistics. Why? Because we don't know the underlying mechanism. We need to use statistics to modeling the observations and the latent effects. So that's why statistics becomes so dominant in biology. So I listed a bunch of topics where statisticians can make huge impact. But in this talk, I only will focus the 3 of them, which is my main research agenda in the last 2 years. So first is watermarking. So watermarking is basically to detect whether text is generated by AI or by human. And second is alignment. Alignment basically is a way to align human's preference, AIM's preference with human preferences. And third is model evaluation. So we want to design a provable, a trustworthy approach to understanding whether the model is good or not. Okay, so this will be helpful for us to design to provide guidance for the design of LLMs. Okay, so I will do in the next, I guess I have 35 minutes, 37 minutes in the left. So there's a lot of materials I hope to deliver, but I think time is not enough for me. So instead, I want basically to highlight the intuition and the motivation from a statistical perspective. And all the technical details will be omitted. Okay, so the first part is watermarking. So this is joint work with bunch of many people, wonderful collaborators. But in particular, I'm grateful to my postdoc, Xiang Li. So he's the lead author of these 2 papers. By the way, he will be on the job market at the end of this year. So we know that, so this is an open secret, right? So many of us are using language models. Students are using language models to do their homework. They are getting better every day. And a little bit embarrassingly, many researchers are also using language models to write conference peer reviews, right? And this is an empirical study from Stanford showing that actually about 7 to 70% of the peer reviews on open review are written or modified by AI. And this fraction will only increase in the future. So this is an even more embarrassing story. So this is a published paper, and I take a screenshot of the official version online. And this is the first line of their paper, and maybe this is a little bit small for you. Let me zoom in, make it larger. So look, it's a smoking gun, right? And so it's clear that this is AI generated. Maybe the author just used their language model to polish their paper to kill typos, but this is very embarrassing. And later this paper was withdrawn. Okay, so it looks like there's a really need to detect AI-generated text from human-written ones. But actually, this is also needed for these AI companies for themselves. Why? Because so this is a Nature paper last year showing that if you train an AI model on synthetic data which were generated by another AI models, and you repeat this process for multiple times, and then this model will decline. It's called a model collapse. The model performance will decline. So this is a real business to let lots of people to clean data, to discard data which looks like suspicious, looks like AI generated. And many researchers are working on the phenomenon of model collapse, including David Donahoe from Stanford. So there's also a need for biosecurity using watermarking, to detect whether some protein is AI generated or not. So there's already lots of research, but this piece of research is mostly based on some linguistic patterns of human language. But in the long run, these approaches will not work. Why? Because as models' capacities increase every day, LLMs has the ability to mimic our style, right? They can learn our style. So in the long run, looks like it's hopeless. Looks like our internet will be full of this AI-generated text. Okay, so now let's look at the good thing that there is an approach called watermarking. So this approach was introduced by computer scientists from University of Maryland. So the idea is very simple. LLMs are probabilistic. Okay, probabilistic, essentially statistical. And we can control how they generate each token, each word by ourselves. So look, the idea is that we can use pseudo-randomness to generate each token, the text. And based on the dependence between the pseudo-randomness and the observed text, and we can say this is AI generated. If there's no such dependence, this is human written. Okay, so this is a rough idea. And since 2 years ago, there's an increasing line of research in watermarking, but mostly it's done by computer scientists. And every few weeks, there will be a new watermarking scheme. And the US and China are the 2 leading countries in this AI race. And from the US side, and Biden passed his AI executive order and pledged that these AI giants, including OpenAI, Google, to watermark their content in the next few years. On the China side, so this is what I take a screenshot from some news and in China, and there's also motivation to use watermarking and to detect whether text is generated by AI or written by human. Okay, so now from a statistical perspective, what can we do? First of all, of course, we need to ask the right statistical questions. What are the right questions from a statistical viewpoint? First, we need to distinguish between 2 types of error, type 1 error, type 2 error. Type 1 error, it's false positive. It's written by me, by a human, but mistakenly classify this as AI generated, type 1. And type 2 is the opposite, okay? And why do we need to care about these 2 types of errors? Because in statistics, we often first control the type 1 error, and then we compare 2 errors, the type 2 errors, and we want to choose the scheme, which has a smaller type 2 error. And meanwhile, we also want to make it more robust against, for example, human edit. Okay, so I just last night I asked ChatGPT to write some short paragraph about the Tsinghua statistics department. So this is what ChatGPT wrote. And why do we need this example? Because we need to introduce the concept of tokenization. So tokenization is a process to break down text into small pieces. Most often, a token is just a word. For example, university, department is a token. But sometimes, a single word can be split into 2, 3 different tokens, like Tsinghua is split into T and another 2 tokens. But in this talk, we can just consider a token a word. There's no difference between token and word in understanding in the talk. So as we record that LLMs are autoregressive. Each time it wants to predict the next token. And the possibility is K. There are K many different tokens. K can be 50,000. For DeepSeek, can be 128,000. It's huge, it's large. So in statistics, this is a multinomial distribution, right? And each time there's a vector P, PT, is a k-dimensional vector. It's denoting the distribution of the multinomial distribution. I sample the token following this probability distribution. And this P is computed by a transformer. But we can, in this work, we cannot assume P is known. Why? Because P depends on many things we don't know, including system prompts. So this is a way to generate a token without watermarking. So now we want to generate the 7th token, and the probability distribution is 25%, 70%, and we sample following this multinomial distribution. Okay, now there is a watermarking. When watermarking is imposed, now the selection of the token is given by this decoder S. Decoder in general is a deterministic function. Sometimes can be randomized, but in general it is deterministic, depending on the multinomial distribution and also its pseudo-random variable. This pseudo-random variable is given by a hash function, depending on some text you observe. Anybody can see, including the student and the professor, and a private key. The private key can be only accessible to the professor, not the student, okay? Only the professor can compute this hash function, not the student. Okay, so now we see that basically every watermark corresponds to a sampling from a multinomial distribution, right? We hope that leveraging the randomness from this pseudo-random variable, the resulting distribution of the token will following the original multinomial distribution. And then in statistics, what's the most well-known sampling scheme from multinomial distribution? I guess this is the Gumbel-Max trick. So Gumbel-Max trick is to sample IID uniform distributions, okay, K copies, and then you take log of the uniform distribution divided by P, the corresponding probability for each index, and then you want to select the index which maximizes this fraction. So this will follow the multinomial distribution. And a computer scientist called Scott Aronson, who was visiting OpenAI 2 years ago, he proposed this watermarking scheme. So basically, to select a token which maximizes fraction, log of U divided by P. Okay, so why there could be a evidence to select to detect AI generated text? Look, so here we want to maximize this fraction, right? Although P is unknown, but if in general, if we want to maximize the fraction, and then the numerator usually also tends to be larger because the selection effect, and then this U will be stochastically larger than its original distribution, which is uniform. So you can make a histogram of this U for each token, and if this stochastic larger than uniform, then it's evidence for AI generation. So this has been internally implemented at OpenAI. So last year there was a discussion at on Wall Street Journal about when the OpenAI should release this technique. It's not yet, but maybe it will be done in the future. So basically, every tech giant has their own watermarking scheme. Like Google DeepMind has their watermarking scheme, which was published in Nature last year. Okay. So now let's go to the statistical elements. So now we want to formulate this statistical problem. So under the null, this is written, and when this is written, they are basically independent, okay? And the token and the pseudo-random variable are independent. But when this is AI generated, then they must satisfy this equality, okay, by the decoder. So the data we can leverage is the pseudo-random variables and the token, everybody which can see. And but meanwhile, And the P, the multinomial distributions are assumed to be unknown. Okay, so this is the distribution. So you see, under the null, they are independent. The token and the pseudo random variables are independent. Okay. Yeah. Pseudo random variable given by hash function. So it's pseudo random variable, but statistically, we basically consider this as a fresh general random variable. Okay, and because it's hypothesis testing, we can first use the Neyman-Pearson lemma. But unfortunately, the Neyman-Pearson test depends on what? Depends on the unknown multinomial distributions. We don't know. We cannot use it. So instead, we propose an idea of pivotal statistics. So pivotal statistics is basically the idea to make the distribution independent of something you don't know. So we propose YT as a function of the current token and the current pseudo random variable, such that its distribution is independent, does not depend on the unknown distribution PT under the null. Under null, it will have a fixed distribution. Under the alternative, now this distribution will depend on P. Okay, so the good thing of pivotal statistics is that now you can choose any score function of your choice. Okay, and this score function under null, because each component under null will have fixed distribution, and the between is independent, and then you know the null distribution of this test statistic. Okay, if you observe a test statistic too large or too small, then you can reject it. Okay, so now I skip all the technical details. I apologize, but what we can say is that using large deviation theory, we can prove that the type 2 error, while fixing the type 1 error, the type 2 error will decay exponentially. And how fast it decrease depending on the number of tokens. And as you have longer text, you will have smaller type 2 error. So the rate depends on this minimization form, okay, minimization form. And here inside, this is the worst case moment generating function. So finally, yeah, good question. So for example, I skipped lots of details. So for the gamma max watermark, actually we can use the variable. Maybe I can go back to the gamma max watermark. Yeah, for the gamma max watermark, a pivotal statistic can be selected as this one. Why? Because under the null, although it's under selection, under null this is selected by Huemer, okay? But Huemer, of course, we don't observe any private key. So our selection is biological. It's independent of the mechanism of the transformer. So this one will still follow the original uniform distribution. But when this is really AI, this is selected by this rule, and then this distribution will follow a mixture of beta distribution, will be stochastically smaller than uniform. Excuse me, stochastically larger than uniform. Oh, U is given by some hash function. So everybody can, it's not everybody. The professor can see. As long as you have the private key, you can easily compute the hash function. Yeah. So this is public, and this is private, only accessible to the trusted party, like the professor who are teaching a course. Hash function, the function is public. The form of function is can be released. Yes, yes. Oh, so yeah, there's no such yeah. Yeah, suppose I also write something like this, okay? It's written by my biological process, but we can still compute it. It's not used in the generation, but we can also mimic the process. We can also compute the hash function, because this is a function depending only the text we written and also the private key. Yeah. So we can also perform it. And once you do it, and you will find that this is not significant. It's to follow the original uniform distribution, not the selected one. Yeah, but if this is AI generated, then this statistic will be stochastically larger or smaller than original distribution. Yeah. Good, thanks for question. And I skip tons of details, technical details, apologize. But later what we can see that we take a minimax perspective and we consider a class of the multinomial distribution. And the nature choose the worst case, but we want to choose the best case, right, using score function. And what we can show that the best score function under certain class looks like this. It's a little bit ugly, I apologize, but it's analytic, it's easily computable. So data is basically a pseudo temperature parameter, usually taken to be 0.1 or 0.01. Instead, Scott Anderson proposed this statistic, and some people from Stanford Computer Science proposed this score function. And this is more intuitive than ours. Why? Because under now, this is uniform for the Gumbel max watermark. Take log of u of what? This is exponential function. It's exponential distribution, right? Negative exponential distribution. And then the statistic finally will become what essentially becomes the gamma distribution. So it's very easy to understand. Okay, but the good thing that for us is that our rate is uniformly above their score function. Okay, our score function is red. We have a higher rate uniformly. A high rate means that we will have a faster type 2 error decay. Okay? And we also have done real experiments for OPT, a small language model. So basically, our type 2 error, we all control the type 1 error by definition because the score function is known. But we all control, regarding the type 2 error, we will have a smaller type 2 error compared to all the other methods. Okay. So there's lots of research surrounding watermarking schemes. And yeah, I only list a bunch of them. But now let me use the 5 minutes to quickly scan through the first two topics, robust detection and the proportion estimation. Robust estimation means that, okay, in reality, we will modify the text, right? When you modify the text, and then the hash function will be gone. Hash function is no longer valid. And in this case, and the signal is corrupted. And what we use to model this process is to model that for some fraction is still AI generated, but for some fraction is written by Huemer, it's modified by Huemer. So it's a mixture model. For this mixture model, and what we do is to use some classical statistics in mixture detection. And what, for example, what we use is this goodness of fit. So it's a little bit technical, but what I can say is that we basically compare the null distribution of this statistic. Null distribution, this is R, and we also compare the empirical distribution. Compare the null distribution and empirical distribution, but we don't know the threshold, right? Where should we compare the difference? And what we do is to use a scan statistic to maximize the difference, take a soup. So this is very similar to the high criticism idea proposed by Professor Donahoe and Jing. So ultimately, what we can show that our under the null, our performance is the same as before, but under adversarial edits, and our method will have a higher power than the other methods. Okay, so this is the only method. Now let's formulate some statistical theory for it. So what we do is to formulate this sparse mixture detection model. So n, the number of tokens goes to infinity, and the fraction also decay polynomially. And also the probability will become closer to 1, meaning that the entropy will decay in also polynomial way. In this case, there is a phase diagram. The phase diagram is that if Q and P is above 1, and then null and alternative are basically the same. There's no way, it's information theoretical. They are basically the same. There's no way to separate the null and alternative. But on the other side, and the null and alternative can be separated asymptotically. But this is information theoretical. The question is that, is there any method to separate them? And our goodness of fit method can do it. So the type 1 error, both type 1 type 2 error will go to 0 as long as in this regime. So this means that this goodness of fit is the best it's information directly the best possible method. Okay, so this is our experiments, by the way. So our experiment basically fits our simulation. In our experiments, and this is the phase diagram. Here it's the success detection. The darker the region is, meaning that we are more successful in detection. So basically, the color matches the theoretical prediction. So now let me because I need to have other two topics. I only have maybe 2 minutes for this part, for proportion estimation. So proportion estimation is basically to understand how much fraction is contributed by AI, okay? Maybe in 10 years, or in 5 years, basically all the homework assignments from students will be partially assisted by AI. Then in this case, the question is that the fraction of AI is 90% or 10%. I think as an instructor for me, like me, 10% is okay? But 90% looks a little bit worrisome. So then there's real motivation to estimate epsilon. Epsilon because it's a fraction where it's contributed by AI. Okay? And then we can use again, it's the mixture model. This is written by human. This is by AI, okay? And we want to estimate epsilon. Okay, and now we can use the notation. So here the notation is that F bar is the overall probability distribution, okay? You observe everything, okay? But in reality, there could be two mixtures. The not mixture is known, the distribution, because we know it's pivotal. But the alternative is unknown, right? Because why? Because the alternative depends on P, okay? I don't know how many tokens are written by AI, and I don't know PT. I don't know the multinomial distribution. I know nothing, basically. And the FP is unknown, so that's the difficulty, okay? If I know FP, and then we can easily find epsilon, because for any test function, epsilon must satisfy this equality. It's very easy. But the thing that we don't know FP, okay? We don't know FP, so that's the issue. We don't know. So that's the difficulty. And meanwhile, the test function can be arbitrary, but some will have lower variance, some will have high variance. Which one should I choose? I don't know. So then what we do is to use synthetic data. The idea of synthetic data, basically what we do is to mimic the text we observe and generate text of similar style. And hopefully the underlying multinomial distribution will resemble the original multinomial distribution, which is not observable. Okay? And then what we do is that, for example, we can just ignore this contribution. In this case, we basically add a constant number, a positive number on both the numerator and denominator. And then we will overestimate it, right? So this will be up biased. On average, will be larger than true fraction. Okay, and now we can also, for any indicated function means that if your U is smaller than some threshold, it's 1, otherwise it's 0. So this is very easy, but it's not optimal. So what's the optimal test function? Look like this, okay? The optimal test function is a little bit complex, but the idea of finding it is very simple. It's to compute the variance of this expression. What's the variance? And by minimizing the variance of this thing, and we can analytically find the optimal test function, V. Okay, these are our simulation results, and our optimal test function, okay, achieves the minimum mean square errors across all the true proportion epsilon. Okay. Okay, so far so good. I have 10 minutes. Everything is on schedule, but I will only touch. Yeah. Okay, so the generation of the watermarking text will entirely depend on OpenAI. So they have to agree to use watermarking in the sense, yes. Yeah, basically they needed to use the Gamble Max trick to generate the next token following the multinomial distribution. But as a professor, I only need to compute the hash function to evaluate the statistic. So this only involves the text, which is public, and also the private key. So the private key must be passed through, for example, a university to the instructor who is teaching the course, for example, right now. So yeah. Yeah. The keys, use the OpenAI, and it should be passed the original key to me. And for security, I asked some people who are doing crypto recently. They said in reality, they need to constantly update the key. For example, every few months, they need to change the key because there's a risk that it will be released. Yeah. Yes, passwords you need to update every 6 months. I haven't updated for many years. Yeah. So this is alignment. Again, this is joint work with many wonderful collaborators, and my postdoc Jian Congxiao is the lead author. By the way, he will be also on the job market very soon. So this is the famous ILHF, and now let's go to the third step. The third step is basically to pass the knowledge from the reward model, which can be thought of as a teacher, to the LMs you want to fine tune. Okay, so basically you want to use reinforcement learning to let the language model to output a response, which is good according to the reward model. Okay, so what is a reward model? Then this is famous. Okay, so this is a Bradley-Terry model for pairwise comparison, and so basically we use the exponential of the rewards to evaluate the probability whether apple is preferred over orange. Okay, so this is really used by OpenAI to train their reward model in their InstructGPT paper. Okay, and but however, what they do is a little bit not statistical sounded. Why? Because they only just want to maximize the expected reward. Expected reward R is a function of the question X, and Y is the response. Okay, so the reward is high. If R is high, means that the reward is preferred. Otherwise, it's small. Okay, so this is maximized over all possible distribution Y generated from the policy distribution, parameterize the weights, and also conditional on X because it's conditional distribution because different prompt will have a different distribution of the response. X is conditional, X is fixed. Yeah. So, but unfortunately, empirically, people found that the majority will get too much, meaning that in practice, only 51% of people prefer Apple, but after this fine-tuning, reinforcement learning, 51% will jump to maybe 60%, 70%. So this is an empirical study. So when I first saw it, I consider this must be some opportunity for statisticians because this is a bias problem. We need to debias it. And why this bias could arise? Because this is really because here between apple and orange, right? Although the apple's reward is slightly higher than orange, I would rather to put 100 probability on apple only to maximize my reward. So, but the result outcome is not good because the minority will go away. There's no minority voice. Okay, but however, women's preferences are diverse. Okay, and even from the OpenAI's original paper, they found that about 1/3 of the time, even their professional human labelers won't agree with each other. Okay, and many questions, many prompts about like personal choices, right, between coffee and tea, basketball and football, right? So this is certainly something we statisticians can make it better. So when I first saw, so I attended John Schulman's talk 2 years ago. So he also recognized this issue. He was a co-founder of OpenAI, but the concept, the notion he gave for all these phenomena is over-optimization. Okay, so it looks like they don't have enough statisticians in their team. So to me, it's a really statistical problem. But what they propose to solve it is basically to early stop. Okay, you don't solve this problem, don't overtrain the problem. But if the bias is there, if you early stop, you only maybe reduce the bias by half. The bias is still positive, still there. So what we propose is to use a regularization term. So regularization term is basically to add a function of the policy distribution. And now we want to maximize the adjusted reward, not the original reward. Okay, it's R plus R, small r plus big R. And hopefully we would like to match the original BTL distribution. The maximizer of the distribution of this thing will follow the original BTL distribution. And in this case, if so, then we basically match the distribution of the reward model, which is good. And I skip all the technical details. What we can show that, yes, there exists such regularizer. And this is an if and only if condition. And this regularizer must take this form. Okay, so this is basically will give you entropy. And these two terms come from the integration by part process. Okay. So basically, the proof of this thing only took Jiancheng and me like 1 or 2 weeks, but later we spent like 6 months to do the experiments. Okay, and let me also briefly elaborate. Here, if we want to maximize the reward, we will be only a little bit narrow-minded because we only want to output the highest, most promising apple, for example. But this entropy maximization will give the counter effect because now we want to diverse our output, right? So this is our proposal. We hope to do this preference matching ILHF finally. And we took about 6 months to do experiments because we are statistician in background, didn't have any like GPU computing, and Jiancheng was very diligent. He learned so much, and it took 6 months to do experiments. So finally, what we can show is as follows. So we fine-tune a 1.3 billion parameter small language model. So this is the original divergence between the reward model and the fine-tuned LLM for using the OpenAI's approach. And the smaller the divergence is, the better the alignment. Okay? So what we can do is choosing some parameters, we can reduce the divergence by like 20%. And later, we made some friends who are a little bit richer. So they can afford to like provide 6, 8, 100 for us to do the experiments. And we run a Llama 7B. And what we can do is to reduce the divergence by 30%. So our hypothesis is that if we got more GPU computing, and we can further reduce the divergence. Okay, so maybe let me quickly skip this part. So this is basically to examine whether there's something wrong with the second step of OpenAI. So this is to train a reward model. Okay, and but however, for reward model, there is a phenomenon called transitivity. Okay. If the majority prefer A over B and B over C, then it must be prefer A over C. Okay, this is transitivity. But however, is this really the case? Perhaps not, because this was discovered by the famous French mathematician, the philosopher, and the politician Condorcet. So he found that actually human preference is not transitivity. Why? What's the minimum example? Suppose Alice has preference A, B, C, and Bob and Charlie, and then we will find that about 2/3 will prefer A over B, and 2/3 prefer B over C, and another 2/3 prefer C over A. So it's a cycle. Okay, and but however, is this the universal phenomenon? Is this really the case? Okay, so what we can prove that the probability of this cycle will approach 1 exponentially. Okay, exponentially. So this means that in practice, cycles is everywhere. Okay, everywhere. So this shows that OpenAI's approach using reward model is fundamentally flawed. Fundamentally cannot capture some of the human preferences. It's fundamental. Okay, and we also extend this result in social choice theory because later we found that this is related to some literature in economics. Okay, and later we consider approach which is developed by Google called alignment using Nash game. So basically, we have 2 LMs who are competing to each other, who each want to generate a response preferred over the other. Okay, it's a game. It's like AlphaGo, and we want to compete. Let the language model compete each other. 2 language models compete each other, and then the issue is that will they collapse to 1 response? From a statistical perspective, we hope that there will be a diversity, and it will not give always a same response. So what we can prove that actually it will not collapse the response. It will not collapse only if there's no Condorcet winning response, meaning that there's no response which is preferred by all the other. And the probability of such bad event happens polynomially small. Okay, so this is what we can prove. It's polynomially small. So this means that in general, Nash game, okay, Nash learning from human feedback is statistically valid. So we train a small language model and show that our method will basically compare favorably with all the other methods. So good, I have 2 minutes, good, for the last part, evaluation. And again, this is done by wonderful student Xiang Li. So again, okay. So evaluation, why is important? Because now every day there will be a new language model showing that it has the highest SOTA highest performance on all the benchmarks. But when you try yourselves, it's not always the case. Okay. So Andrei Karpathy is a famous AI researcher. He tweeted that he no longer trusts this model evaluation. So this here, we were inspired by the two great minds in statistics and computer science, Brian Efron and Turing. Okay, Brian Efron used the idea to estimate how many words did Shakespeare really know. Of course, you can scan all the words written by Shakespeare, but it's possible Shakespeare knew some words, never had a chance to read it down, or maybe some poems got missing in the history. And Turing also used this idea to estimate how many sequences of the Enigma by German army who were not observed. Okay, so basically he used the Turing estimate basically to correct the Enigma during the Second World War. So I skip all the technical details, but what we can empirically show that, so this is also quite valid for language models. We can use this method to estimate how many theorems, okay, how many rare diseases did a language model know, but it never had a chance to let you know after a finite number of prompting. Okay, so basically this is the prediction, the red prediction, and the black is ground truth. So the prediction and the match the ground truth quite well. And as a math background person, and we also language models, how many theorems did it know? And also similar story to match the number of theorems, match the truth and the ground and the estimation pretty well. But now let's use it for ranking language models, because this is a huge business, and I know that there's a startup, recent startup from Berkeley, who actually was using ranking of language models as a business. Okay, so here we rank the language models, these language models, according to how many theorems they know from the highest to the smallest. But however, this is only based on what we see, right? Maybe it's possible that they know lots of theorems, but never had a chance to tell you. Okay, so this is a histogram, and the thing that actually we should not, statistically speaking, we should not omit this thing. Okay, maybe there's lots of theorems which are already there, okay, in the training data set, but never had a chance to be prompted. So what we can prove that basically using, what we can show that using Turing and Efron's estimate to show that actually there's a large fraction of theorems which are not seen, actually. By adding both the seen and the unseen, and now the ranking look like this. Now the number one becomes GPT 4.0, 4.0, sorry, 4.0. 4 becomes the largest. So these two rankings looks like they differ very much, right? So this shows that actually statistical ideas can be really used to better evaluate the performance of language models. Ignoring observations we don't observe is not good. Okay, now let me conclude, sorry. And there's a lot of topics. And for example, uncertainty quantification and machine learning. I didn't have a chance to work it, but I know that some statisticians are working on it. And I hope that there will be more topics where statisticians can make more contributions in AI research. And I believe this is no longer, it's neither the case of the two cases, it's neither of the two possibilities. And then what's the possibility in the future? I don't know, because it really depends on how hard we are working on bridging the gap between AI and the statistics. But there's really hope that I believe that we can tame down AI. And finally, because AI is a way to make our statistics more powerful. And I believe this could be our future. And so this is I wrote a position paper about this talk. And so these are references. And thanks for your time. Oh, yeah, I got it. Yes. Yeah, you're right. We can use a mixture of the real-world model to overcome this issue. But the difficulty, I would think that how can we model a mixture, right? And because we don't know, by definition, a priori, we don't know how this group differ from the other group, right? Maybe we could do a clustering beforehand. Yeah, thanks for the question. Oh, Xinran Li? Oh yeah, I will check out. Thank you. Oh yes, yeah. Yeah, thank you.
对，我们再次感谢王老师。对。
Let's wait for a moment to set up the desk and the chairs. This is the last session and a very special session of this conference. And I think before this talk of Professor Edo Aradi, so we will get started very special the appointment ceremony because Edo has been here with us for more than 2 weeks, right? So already served as our distinguished visiting professor for quite a few days, but this ceremony a little bit delayed. But today, we get together to celebrate this very special event. And I think at the beginning, maybe just ask Jun to briefly introduce Edo's academic achievement. And later on, we will have this signed as contracts by Professor Song Xi. So then after that, we can get Edo's talk. Yeah.
Okay, it is my great pleasure to introduce Edo Aradi here. I seldom say his full name. I just call him Edo. He has been my great colleague and friend for many years. I'm really happy he will take this appointment. And I read there are a lot of words and those things. I don't really want to say that. You can read. I think he impressed me when he first applied to Harvard, and I was impressed by his strong interest and achievements in computational biology, and also broad interest in interdisciplinary research. Other than his very fruitful contributions and results in computational biology, one of his claim to fame is this famous paper. Nowadays, people are still citing this mixed membership stock block model for networks. I think people are still finding that extremely useful for analyzing big data these days. And he has won many awards. He was on the faculty of Harvard Statistics Department for nearly 10 years. And then he moved to Temple. He has, that's one achievement. Another achievement, I think, in my view, is he's the son-in-law of Tsinghua University, so which is because his wife was a former graduate of Tsinghua, and is also my longtime friend. That's his second achievement. And also, he has been a chair and director of the Department of Statistics and Data Science at Temple University, has been working on in many different industry areas as well, related to big data. Of course, only joint work. He never really left academia. So I'm really happy he will be with us for some days every year. Okay, that's my introduction. So Chun-Xi, maybe you will be.
I think we just signed the paper, right? Yeah. Well, what is ceremony? What do we need to do next? Yeah. So please, yeah. So we'll have you sign up. Yeah. Okay. This. Yeah.
So after the appointment ceremony, I think this talk by the Professor Ariadi, so designing optimal interventions. Yeah, let's welcome Edo.
Thank you. Thank you very much. I want to, I want to start by thanking my host, Ke Deng, and Professor Songshi Chen and Professor Jun Liu for appointing me to their wonderful department. I also want to thank the staff for doing a wonderful job in running this conference very smoothly, and the sponsors. And every one of you, this is the last talk. I realize I'm glad that you're still here, willing to hear more statistics. Today I'm going to talk about designing optimal interventions in complex systems. These are a few of the areas over the year in which I worked analyzing complex systems. Today we're going to talk about experimental design. The experimental units for today are going to be households. However, over the years, June talked about some of my work in industry. The motivation for the methodology I'll describe today actually come from a collaboration with Google, the market optimization algorithms group in New York City, when the experimental units were advertisers and they own the AdWords in North America, so US and Canada. And it was also used in collaboration with many other scientists at Amazon in the supply chain optimization technology org, where there the experimental units were software modules. And I'll talk about that a little bit, but mostly I want to focus on a paper I published last year with one of my co-authors, Nicholas Christakis at Yale, on social healthcare, where the units, the experimental units, are going to be households. Okay, and so the way I'm going to go through this talk, I'm going to give you in applied context. I think of myself as an applied statistician, although I try to develop methodology that can be applied across discipline, and I do, to the extent that I can, study theoretical properties of these methods. And then, once I give an applied context, I'll dig into some of the methodology. Obviously, we don't have a lot of time here, so I have some slides which are here for the benefit of people going back, and I'll just say a few words about them, and some slides maybe I'll spend more time because I think they're more relevant to the story I'm going to tell today. Okay, so complex systems are oftentimes boiled down to matrices of covariates and binary matrices of networks, and there's a rich interdisciplinary literature for students who may want to look into this literature. It goes back to the 30s, and statisticians entered around the 70s, and computer scientists took over after the advent of the internet and of platforms like Facebook and LinkedIn and so on. There's also lots of books that can satisfy multiple tastes. They're like pure probability books, there's applied mathematics books, there's social sciencey books, and there's books written by statisticians. And I'm happy to offline guide people if they want to start digging into this literature. These are a lot of the people that contributed to some of these papers that I'm going to briefly touch upon. It's really one research agenda, and so different papers are more on the theory side, more on the applied side. Today, I guess, the methodology side will be about this model-assisted design of experiment with Guillaume Bass, who was a professor at Stanford for a little while, and now is in the UK, and with my collaborator, Nicholas Christakis at Yale, that is the MD, PhD social scientist behind this application. These are some of the people. This is Nicholas down here, and this is Guillaume Bass up here, and the Christian Borg, Jennifer Chase, worked on the graphon estimation part. Postdoc Chen Kai, coming from Rutgers University, derived a lot of the theory behind the optimality results I'll just hint at. And these are other people, Vishesh Karva, Jean Pouget-Abadi, and Dan Sussman, who work on different aspects of the methodology. So the context for today is going to be at the field experiment in Honduras. And as a very complex system, it's not a system of modules, it's not a system of APIs, it's a very real system, but I think it will make for a nice story. So here, the intervention is household-based, and the idea is we want to improve standards of care for newborns. So there are the intervention consists of 15 household visits over 22 months. In this region, there were about 10,000 households, 34,700 people in the census. And the households, there are many papers of what's the direct effect, what's the indirect effect, and so on and so forth. We're looking today at the effect of the intervention of targeting certain households on the non-targeted households. So it's this kind of spillover effect. And there's actually two strategies to target the households. One is just completely at random, and one is by friendship nomination, which you can think of leveraging the network knowledge somehow. Okay, and we want to know whether leveraging friendship in delivering these interventions or leveraging network knowledge is going to be more powerful than randomly nominating households. Okay, and the reason why we're doing that is that oftentimes you don't know the network. It's very costly to map the network, and so this type of algorithm, friendship nomination, is an algorithm that doesn't require you to know the network beforehand. Okay, you essentially you randomly pick a household, and then you do a random walk, a one-hop random walk from this household to another household, and without getting too much into detail, there's something known as the friendship paradox that says, on average, your friends have more friends than you have, or on average, the degree of this one-hop-away households is larger than the degree of the randomly nominated households. And so we were trying to see, to ascertain the extent to which, if you were to leverage a slightly more innovating randomization strategy, you might induce a network effect that's a lot larger than just randomly nominating households in a situation when you don't know the network. Okay, and so that's kind of what we're trying to do, and then we'll talk about the methodology that we used to do that. Okay, the design. So there's two target nomination scheme: friendship nomination versus random nomination scheme. There's 8 levels of treatments. So once you go in a village, you can decide to target 0% of the households, 5, 10, 20, 50, 75, 100% of the households. So we have kind of 16 treatment combinations, 2 by 8. And we have 176 villages. So 16 times 11 is 176. In each of these 16 blocks, there'll be 11 villages. And then within each of these 11 villages, we'll have to target households. So it's a 2-level design, okay? Oh, in this paper, I'm describing roughly is this Chris Takis and I rolled in 2024. Okay, this is just one of the filler slides. I'm gloss over. We started this experiment in 2015, which means we started seeking funding from the NIH and the Gates Foundation in 2012. And we're still collecting data today. So it's a long-term experiment. It's very exciting. We've been in this region between Honduras and Guatemala for like over 10 years with the help of the World Health Organization. And it's been a blast as a statistician having a little part in helping design this experiment. There's obviously a lot of complications, starting from the delivery of treatment. We said it's 15 household visits. Well, this is just a plot that shows you across villages. We have villages where 0% of the fraction of the households were targeted, 5% of the households were targeted, and so on and so forth. This is the mean number of visits. There's also standard deviation. We didn't have 15 visits in every household, in every village. As a statistician being used to work with semi-clean data, it was interesting getting this report back from the field saying, we only could target, we could only, like, the people who tried to deliver the intervention this month were essentially unable to. It's like, oh, why? I mean, how difficult it is to, just go in a household. It's like, well, there was some drug dealing. They were chased out of the village by people with hatchets. Okay, well, I guess that happens too, right? That doesn't happen in a software system, but there's other issues. So now we talked about a complex system. We have a network. We have 26 different ways of measuring connection between people or connections between households. These are some of the questions that we use to elicit this network edges, if you will. You ask who are your siblings, who do you trust, who do you ask, who do you hang out with, who do you go and ask for health advice, who do you borrow money from, and so on and so forth. So we actually had an experiment a few years ago in which our not inability, the fact that we didn't ascertain the network, at this level of depth was really detrimental to the analysis. So in this new experiment, we really went deep into measuring network connections. And the networks were mapped pre-intervention, so about in 2015, and then we mapped them again twice through this app, the Trellis app, which you can think of as a Facebook. In all these villages, oftentimes you have people with similar names, and so we didn't want to introduce noise or having to disambiguate who was whom or who was friendly with whom, and so we had people in the field with these tablets essentially ascertaining social connections. These are the two stages of the experiments that I mentioned before. So stage one, we are assigning villages to treatment arms, and we have two types of nomination schemes, and we have different fraction of the households treated within a village. And then we do this by blocking and re-randomization. And then stage two, we have to choose which households to intervene in each village. Okay, and then that's where the methodology we'll discuss comes into play, because we may have multiple network effects, some causal, some non-causal, and we're going to have a model to assist us in selecting which households to intervene in each village. And I think we did a fair job. We pre-registered our protocol, although it was not an NIH study. So we started publishing what we were doing and why we were doing it and what the primary outcomes were, and so on and so forth. And we stuck to that during the analysis. Okay, this is just a practical aspect of re-randomization. We heard some talks about re-randomizations. We heard about, theory of asymptotics of re-randomization. Here, we have 18 treatment arms, and so, we have 149 contracts we are looking for. Here are the number of treatment arms. So, one contrast could be all the 88 villages that were friendship nomination targeted versus all the 88 villages that were randomly nomination targeted, and so on and so forth. Right? All the 5% villages versus all the 10% villages, and we had the number of covariates, the number of respondents in the village, latitude, longitude, whether the health clinic was reachable during a storm, right? Whether there was how long it takes to reach a health clinic, and so on and so forth, the number of households. And so we used all these covariates for randomization. We actually used a technique at the time, the Gram-Schmidt walk, that was just experimental by Dan Spielman and colleagues that has now been published in JASA, but he was at Yale at the time when we were designing the experiment, and he ran his software for us to generate the re-randomizations. We generate a large number of randomizations. Some of them passed our threshold, and then among those that passed our threshold, we picked the one that we implemented. Okay, and even for the randomization that we implemented, there were some covariates that were not able to balance, and so we looked at why we were not being able to balance these covariates on these, sets of villages in the two contrasts, and oftentimes there was one outlier, but the body of the distribution was reasonably overlapping, so we felt confident that there was a good design. This is just a map between Honduras on the right and Guatemala on the left. These are all the villages, and this is just to give you a sense of, you know, how the blocking worked. The squares are villages where we use the friendship nomination to target the households, and the circles are villages where we use random nomination. And you know, the different colors are the fraction of households treated within a village. And you know, even after you do all this work to assign villages to treatment ARP and do one round of re-randomization, then within each dot, within each village, you do have households, and we had the second round of re-randomization using different covariates to decide which households were going to be treated or not. And you know, we fully mapped the households longitude, latitude. It was interesting to note these are rural occasionally, so that was interesting. And this, you know, we had different reports, one for the Ministry of Honduras, one for the Gates Foundation, like your regular paper about, oh, the intervention worked on the treated, and this is the one paper that Nicholas and I wrote, effect of treatment on the untreated households, and that was in Science, maybe May 2024. And these are some pictures just to give you a sense of what kind of households we're talking about. You know, most of the households had the roof, some didn't have walls, some didn't have windows or doors. And you know, this is kind of the type of villages that we're talking about, so it's reasonable to understand why sometimes during, you know, the rain season you may not be able to go from village A to village B. And these are two of our World Health Organization partners on site with their tablets, you know, going about interviewing people. Okay, and then, you know, I'm not going to describe the results. It's one of the filler slides saying, hey, we did find a big effect of, you know, targeting on the non-targeted households. We have 117 outcomes, so, you know, slicing them in different ways, knowledge, attitudes, practices, there are different kind of responses on a survey. You know, you can see the effect may be different, you know, on things that were practically helping newborns. You know, we had a big effect. On things that people had to learn but didn't have, you know, a practical effect, the effect was actually smaller. Obviously, the main primary care for newborns are mothers, and so the effects was larger on mothers. And then, you know, we measured spillover, you know, outcomes for which had spillover effect, non-spillover effect, and so on and so forth. So that's, you know, you can read the paper if you're interested in these kind of things. And the mental model that we had was that if you do target households in a more innovative way, you get a larger spillover effect, and that's what we found. Of course, there was a lot of heterogeneity in the outcomes. Here is behavioral adoption between wave 1 and wave 3, so over 5 years. And you can see at the top right, there were outcomes like, you know, women should be older than 18 to have a first child, are things everybody knew. And so the effect was pretty much 0. And then there were very difficult concepts to transmit. For example, retaining the placenta, retained placenta is a danger sign at delivery. And so people didn't really learn anything about that. But then in between, there were a lot of outcomes for which, you know, there was some learning, there was some adoption. And in particular, here we're trying to show an effect of, you know, how much savings could you get if you were to use friendship nomination? You know, for example, in the saturated villages, in the villages in which we had 100% of the households treated, there was a certain adoption, and that's kind of the gold standard, if you will, right? And then the question is, well, you know, how much of a fraction of the household you need to treat to obtain the same behavioral adoption that you see if you were to treat everybody. Okay, and that's how we measured how much better friendship nomination was with respect to random nomination. Okay, so enough about the experiment. You know, data is available. I already talked to a bunch of students and faculty about collaborating on, you know, different methodologies to analyze the data or different practical analysis of this data. We are very open to ideas. So that's why I wanted to give you a little bit of a preview. Now we're gonna talk about, what complications happen if you're trying to design an intervention on a complex system, in particular, dealing with the network. And then we'll talk about the methodology that we used across this experiment, Amazon and Google, and then I'll hint at many open problems that we have, with that methodology. Okay. So the main, I guess, complication that we can think about is if you move away from individual treatment response, or SUTVA, which is basically a stable unit treatment value assumption. So the effect of an intervention on unit I, on unit I, on the household, on the ith household, is only whether or not you treat the ith household. Okay, if you treat any different household, there's no effect. If you treat the jth household, there's no effect on the outcome, on the behavioral adoption, the ith household. That's the typical assumption in causal inference. Whereas when you have a complex system, the next step in complexity is this notion of exposure. Okay, and so yi here is the outcome. Think of behavioral adoption on household I. Z sub I is an indicator, is a binary treatment, whether or not you treat household I. And then E is this exposure function that says, think of it as binary exposure, right? Whether or not some neighboring n sub I is a set of neighboring units for unit I, and Z n sub I is a subvector of whether or not any of the neighbors were treated, and you have to compose that somehow, with this exposure function. So if you think about the simplest possible notion is this binary exposure. Unit I, the household I, is exposed if it has at least one neighboring household that has been treated, right? And so the number of potential outcome goes from 2, whether or not household I is exposed, to 4, because now the unit can be exposed or not exposed and treated as untreated. And so here, the control unit, unit I, is the focal unit in the middle, and it's untreated and is not exposed, right? And this is the typical treatment. Unit I is treated, but is not exposed. And so these are the two kind of situation you would find, right? Or you would assume, I guess, in the potential, under SUTVA. And now if you move up and you think that exposure may be a factor, well, now you need to worry about whether unit I is exposed, so itself may be untreated, but at least one of the neighboring households is treated, and then it may be treated and exposed. Okay, and those are 4 different potential outcomes. Okay, and what happens is that, if you think of these 4 situations as 4 different colors, black, blue, red, and purple, right? What the typical randomization strategy does controls, the number of zeros and ones, right? But if you do have a network and you do assume that exposure matters in, the potential outcome functions, then, if you're controlling for the number of zeros and number of 1 up here, number of treated, the number of untreated, right? You're not controlling for all the different colors, for the fraction of nodes with different colors. And that, that's an issue. And so what we need is find the ways to randomize controlling exposure, okay? And so that's where all the literature has been going, and there's different assumptions and different ways of doing that. And there's also different causal effects, and we're just interested in disentangling causal effects from non-causal effects. Okay, so this is the effect of having the unit I treated or not treated and exposed or not exposed, whereas here is a different function, right, that tells you that, the outcome on unit I, the behavioral adoption, may be just a function of not the z's, but the x's, where x's are covariates. Okay, and covariates could also be the neighboring covariates, but these are non-causal effects, because in this different function, although it's the same yi, this could be f, this could be g, to be more precise, there is not a function of the intervention. It's not a function of the z's, okay? And so now we're gonna talk briefly about this methodology that we developed and that we leveraged. Okay, so before jumping into it, I should say I'm going to talk about model-based, and I'm going to say, in my situation, in my application, basing the intervention or deciding which units are treated and untreated using a model is bad. Now, if you're a physicist, right, and you trust the gravity and you trust thermodynamics, it's fine to trust the model, right? But in the applications that I have worked on, in particular, this application I'm describing today, socioeconomic systems, there's a lot of variation. We don't really know the mechanism, the causal mechanism underlying, adoption, right? We can only have simple models that hint at how adoption may work, and so we need to do design-based, optimal, design of experiments, which means we have to find an optimal randomization, or we have to randomize according to an optimal distribution, and that's the Fisher-Kempthorne kind of school of optimal design. And typically you use model-free estimators like a Horvitz-Thompson estimator, or a difference in means estimator, or stratified difference in means estimator, and you look at properties of the estimator with respect to the randomization distribution for finite n. Okay, and so that's what we're doing, and it's the same if if your unit analysis are advertisers, or if your unit analysis are software modules. Oftentimes when we look at AI, for example, people these days are studying scaling laws, how this AI system scale with the number of parameters. Well, they always have a simpler model that is an approximation of this black box, and they study scaling laws mathematically for the little black box model, right? And so even though an AI box is a man-made system, the amount of randomness in the way we study these black box models is always high. And so when you do experiment, for example, determine empirically the scaling laws, you're still going to do randomized experiments. Okay. All right. So, well, I'm going to skip this. This is basically, model-assisted design is using a model-free estimator, okay, and impose model-dependent constraint on the randomization. That's what we're going to do. And so if the model is correct, well, that's great. Model is never correct. But if the model fails, right, or the extent to which the model fails, we still are going to guarantee unbiased estimate of these causal effects. We're going to pay a price invariance, and that's a good place to be if you are an applied statistician. Okay? Because hopefully you can elicit a good model and get a more efficient experiment, but you're still going to get an unbiased estimate. Okay? So this is the pipeline for the model-assisted design. You basically have an inferential target and an estimator that have been given to you. In a clinical trial, you can't really deviate from difference in means. If you're working at Google, the estimator is encoded in their software stack, and maybe Horvitz-Thompson, maybe difference in means, but the estimator is given. You can't play the game, let's find a more efficient estimator, right? So the way that in practice this works out is you can posit the simple non-trivial model for the outcomes that may hint at the causal mechanisms that you're trying to estimate. And then you can compute the mean square error for that estimator that's been given to you with respect to this outcome. And this quantity, the conditional mean square error for your estimator with respect to the model, right, is basically a rudder that tells you which re-randomizations you should trust and which re-randomization are bad, okay? And so you're not doing balancing based off covariates alone. You're looking at this conditional MSE to find new quantities to balance on. It's as simple as that, okay? And it's a simple calculation that you can do, and the fun part in it is to work with your applied colleagues to posit a simple non-trivial model for the outcomes that may be reasonable to them, right? And so this is just a super silly example, just to fix idea and be concrete. Think of the outcomes, Y as the propensity to adopt a behavior, and Z is binary, whether or not the household I was intervened on. X could be, the amount of knowledge, right, that goes in, right, into your household, right? And all you are saying here that the propensity of adopting a behavior if you are non-treated is a function of the amount of knowledge in your neighboring households, right? And if you were to be treated, right, you are, their propensity to adopt the behavior is beta units more, whatever that is. So this is not, I'm not introducing this, effect of treatment on the treated yet, because YI, when, this is only a function of whether the unit is treated or not, so don't be confused. This is just the simplest possible case to show you what model-assisted design does, and then we'll introduce exposure later, okay? And so here I have, somebody gave me this difference in means estimator, and this is my simple model, and this is the conditional MSE I'm talking about, right? And the conditional MSE is just bias square plus some variance terms, but now, interestingly, these variant terms depend on the network, okay? And so, for example, here, depend on the average number of shared neighbors between treated units, the average number of shared neighbors between untreated units, and the average number of shared neighbors between a treated unit and an untreated unit. So, so you can look, and here the bias depends on whether on the average degree of the treated minus the average degree on the untreated. And so somebody could simply say, oh, if I want to find a randomization that, is better, given that this is the conditional MSE, I could just find randomization for which the average degree of the treated is the same as the average degree on the untreated, so I get zero bias on average, okay? So, and that's what we do. Basically, we use that conditional MSE to find tiers of randomizations, right, in a different way that Ke, for example, is doing that with a prior. And, these are the balanced randomization. Number of treated is same as the number of untreated. We call this unbiased randomization. Average degree of the treated is the average degree, is same as the average degree of the untreated units, and so on and so forth. And so we re-randomize within these tiers. And of course, we have simulation that will show if the model is true, that's great, right? What I was promising, or what is an interesting theoretical result, is that this way of re-randomizing within tiers of re-randomization, where the tiers are based on minimizing factors in the conditional MSE, is so-called design unbiased, meaning re-randomizing or sampling a random, right, a constrained randomization, still give you an unbiased estimate. And that is something that we can prove in this case. But more interestingly, we understand where this property comes from, right? And the property that comes from two kind of notions of symmetry. In this particular case, and we can generalize, but in this particular case, we have a difference in means estimator. And if you think of a binary vector Z that tells you who is treated, who is untreated, the opposite binary vector 1 minus Z is simply swapping everyone's household that's treated to being untreated, and every household that's untreated to now being treated. So it's literally, right, flipping zeros and ones. And what happens to this estimator is symmetric to these swapping operations, right? So you get the same amount of bias but a different sign, okay? So that's a property that you can prove on any estimator that you're using. And now, if this estimator has this symmetry, in order to guarantee zero bias on average, you just have to make sure that the set of constrained re-randomization you're using is closed with respect to the swapping operation, right? And so now we're looking at the constraints, and we're wondering, are the constraints symmetric or closed with respect to the operation? And if you just go back, now look at the unbiased randomizations. If I were to flip everyone in control to treatment, everyone from treatment in control, the degree of the treated wouldn't change, the degree of the untreated wouldn't change, and so this constraint would still be satisfied, right? And so in order for these theoretical design unbiases to hold, all you need to do is to look at the constraints that come out of your conditional MSE calculations that you're willing to apply in practice, and make sure that they are symmetric with respect to this operation, and also prove with a pencil and paper that your estimator is symmetric with respect to this operation, and you can do that, okay? And so now this particular application, we had a slightly more complicated model. And all you need to observe here is now I have this notion of treatment and I have this notion of exposure, right? It was binary exposure. And here now I have the units were treated in a notion of exposure. And on the right-hand side, I still have some possible effect, due to homophily, due to covariates. I now have two possible different effects, beta 0 and beta 1, due to the exposure, right? The sum of units that were untreated and they were neighboring. And then I also have this tau, which is, unfortunately, it was beta before. So there was the effect of being treated, okay? But the point is you can come up with a more complicated, more realistic model. You can come up with a more complicated mean square error, maybe for a different estimator, and go through the same notions, and then find re-randomization tiers and re-randomize within those tiers, and that's what we did in the Honduras experiment. Okay, and obviously there's limitations in practice, there's limitations in theory, there's lots of open problems, including we'd love to take the integral of the conditional MSE with respect to the constraint re-randomizations, and that's hard because we don't have parametric control over that space of constraint randomization and so on and so forth. I only have a few more slides. I think don't know who is keeping the time for me. To me, it seems like I'm not at 45 minutes yet. I'm like, what, 35 minutes? All right, well, I won't keep you here long, I promise. I think I'm at 30. Yeah, oh yeah. More plenty. Okay, so now this is kind of, how to do model-assisted design of experiment if you condition on the network. Now, in a lot of applications, you may have not just a network, you can have multiple network. You may assume that we elicited these edges, and so you have uncertainty in the edges, right? And so instead of conditioning on a network, you may want to condition on an estimate of the network, right? And so these are graphons come in. Graphons are the simplest possible generative model that leads to exchangeable edges, right? And it's Hoover, Aldous, Kallenberg. There's lots of people. Bickel and Chen have written about these probability models, but now we found them useful for designing the networks. I'm just going to tell you what they are or how do you generate, right? So think about the Dirichlet process. This is the equivalent in network space. And so the graphon is just this function from the unit square to the unit interval, right? And so, that could be, this is telling you that no matter, well, and the way you generate this network, you sample, you say you have n units, you sample a uniform distribution for each of the units, and then you evaluate the probability of an edge between unit I and unit J by just looking at the height, right, at the value of this curve at UI, UJ. And so here, no matter what UI and UJ I get, the probability of having a connection is the same. So that would be a Neruda-Sreni network, or the probability of a connection is the same. In this particular case, is 1/2. This would be a block model in which, depending on whether the two units are here, the intersection is here, 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 or here, you have no probability of an edge, medium probability 0.4, or a higher probability. And then, this, think about the base measure in the Dirichlet process. This is a very flexible kind of network model. And a very large literature in statistics has been spent into how to estimate these graphons. And this is like the typical strategy, starting from the paper Bickel and Chen, Levina, I think Donahoe worked on it, Carey Prieb, Mark Hancock, so many people, but they all kind of work the same way. So this is your original adjacency matrix, a binary matrix, and it's an unordered object, so it's kind of symmetric to permutation, the model, right? That's what exchangeability means. And so that's what the matrix looks like. The first step is you commit to an ordering. Maybe you sort by degree, you do some spectral decomposition, and so on and so forth. And so here I just sorted by degree, and you can start seeing some pattern that's more defined than here. And now here I have a 500 by 500 adjacency matrix, and all you do a two-dimensional histogram, and now I have 85 bins on the y-axis and the x-axis, and you just compute the average density within each bin. And that's basically how you estimate a graphon. The 2D histogram is a consistent estimator of the graphon, right? And a lot of properties that the one-dimensional histogram has, they translate into two-dimensional histogram estimation of a graphon, and so on and so forth. You can do total variation minimization, so that's how you do it. And then you can do model-assisted design of experiment now, conditional on that estimate of a graphon, assuming your graph comes from an exchangeable family of graphons. Okay, so I'm going to skip a few things. That's fine. All I want to say is that, so then I'll say a modern strategy to do experimental design on graphon is called randomized saturation design. And so the idea is, well, now I have 85 bins, 85 sets of nodes. The randomization distribution is, let's select P1, P2, 85 different probabilities that will decide the fraction of units that I'm going to treat in each bin. Okay? And, you can imagine that being a simple randomization distribution, right? Instead of randomizing 50% of the units, you now randomize maybe 25% of the units, 32% of the units, 85% of the units, and the question becomes, what's the optimal set of fractions of units to treat in each of these bins? And that's the optimal randomization distribution, okay? And so if I fast forward some simulations, we were trying to estimate here the network effect, the effect of treatment on the untreated units, and we, tried different strategy. Cluster randomization, for example, is you divide your 500 units into cluster, and then you treat 100% of the units in half the cluster and 0% of the units in half the clusters. Okay, so it's one way of leveraging this network structure. Or you can do completely at random, so you can randomize, treat half the units at random and half the units you don't treat them, okay? Or you can find, as I was hinting at, the optimal set of fractions of units to treat, say, in each cluster or in each bin, right? And so, it turns out that the optimal randomization distributions, right, are distributions where if you look at the percentage of neighbors treated, that could be from 0 to a certain fractions, right? For some units, maybe a lot of neighbors are treated. For some, only few neighbors are treated. But you're treating as a budget 50% of the units. On average, you won't have more than 60% of the neighbors treated, or less than maybe 20% of the neighbors treated. So here I'm looking at the distribution of neighbors treated, and that's a quantity that hints at how these optimal randomizations are different. The optimal randomization will have very distinct distribution, and multimodal, highly multimodal distributions in the space of a fraction of neighbors treated. And then, that's just visually, then you can actually prove that mathematically. And so, we have a series of paper. The seminal paper, a paper by Jeff Wu in 1981, where he showed that complete randomized design, so treating all these units, 50% at random, are optimal for estimating the average treatment effect. And by optimal, it means that among all the randomization, that's the randomization that minimizes the maximum loss, where the maximum is taken over all potential outcomes, right? So it's a minimax where the max is over all the possible potential outcomes, or all possible sets of potential outcomes, and he's looking for the minimum randomization, the randomization that's best at minimizing the maximum loss. Whereas here we have, you know, model assisted, so there's a model in the mix, and so we're looking for the randomization that's best, that minimizes the average loss, where the loss is the average loss over the potential outcome generated by a model, right? So it's not minimax, really. But then when you know, when you're dealing with model, that's a good surrogate or a good practical, you know, optimality criterion. And then when you look at this criterion, we can show, this was a paper with Jennifer Chase, Christian Borks, and Christina Yu, who is now at Cornell, that cluster randomized design that are optimal for estimating the total treatment effect. And you know, the randomization strategy I just described to you, where you take a graph, you have a estimator of the graphon, right, using the graph in which you collapse the graphon into sets of nodes, right, and then you pick a different percentage of units to be treated within each set of nodes. Well, that's what we call randomized saturation designs, and these are optimal for estimating these average network effects. And so, you know, years later, we finally found some closure. There's still many, many open problems and assumptions that we had to make that may be untenable in certain applications, but at least we have a set of results that is a starting point. And then another set of issues, which is more in the Google, LinkedIn, you know, since we talk about industry world, is, at least in the United States, oftentimes companies will not allow you to randomize advertisers or randomize sellers or randomize customers, because, you know, it's a liability issue. If you randomize advertisers and they're less competitive because they are treated in some way, right? So they participate to auctions that are specialized auctions, they could sue, for example, Google or Amazon. And so because of this legal constraint, this bipartite causal setting, you know, kind of grew out of industry in the US, where you can, for example, randomize the AdWords, not the advertisers, but you really want to know whether you have an effect of advertisers because they're paying more now, right? And so you have a set of randomization units and you have a set of outcome units, and you know which advertisers, say, are bidding on which keywords, and so you do have this kind of bipartite network, and, you know, there's a whole new set of questions or new set of challenges that come up when the units you can randomize are not the same set of units on which you can collect the outcomes, but you understand something about, you know, how they relate to one another. And that's sort of the last open problem that I'm throwing out there. And I want to end by, again, thanking everybody here for being patient and say, well, design of experiments and causal inference used to be stagnant for a while, and I feel, you know, in the era of AI, online platform, online advertising, these two areas of statistics have been energized, and there's so many more interesting problems that may have real impact in the world, both in industry and on global science efforts. And there's many, many open problems I'm happy to point people at and talk about. I'm working on some of them. And, you know, if you just email me if you're interested, I'd love to talk to you about some of them. Thank you very much.
Are there any? Okay.
So you have four kind of design. One's you know, have the network influence. You have everybody now treated as a control, and then you have one household. It's a unit household, right? So it's a household treated, and then the neighbors are not. So from your analysis, which one is more effective? Do you have distinctive treatment effect for the network influence of your study?
You know, that's a great question, and people used to think that, once this effect of treatment on the untreated kind of got some press for word of mouth campaigns and so on and so forth, people focused on that. And then people at Facebook wrote a paper saying this network effect is always a secondary effect to the direct effect. So if you can afford to treat so many units, you should do that. If you can't afford to treat that many units, maybe you can treat a smaller set of influential units and hope that there's a secondary effect on everybody else. And so for a while, that was the mental model. And so to answer your question, well, it's better if you have a budget to treat directly who you want to treat. If you don't have a budget, it's better to treat influential units. But then more recent papers have shown that oftentimes the direct effect may be still smaller than the direct effect, but opposite. And so now, you need to study network effect itself. You cannot just assume that because you have a positive direct effect of advertisement on spending, that will be the same if you now treat the, influential units, and they'll generate more spending just by spillover. So it's complicated, but in my experience, treating a unit directly is always more effective, right, than treating a unit indirectly by treating friends. But it's a very empirical question. Depends, like application by application. Yeah.
In your study, you adjust the strategies. You have a fixed design, or during the course of the survey, you change. You have adaptive change of your strategies. For example, the percentage of the you have certain percentage, right? 5 levels or 8 levels, right? 8 levels. Do you change to keep this fixed, or you keep changing this?
So we learned. That's a great question. So, for example, think about treating 75% of the units, right? And I treat them with strategy A or strategy B, right? Well, if I look at the neighbor of 70%, 75% of the treated units, that's everybody else, right? So I don't have any heterogeneity in the sets of neighbors, right? And so we learned that, if you treat too many units, then the strategy, choosing strategy A versus strategy B won't make any difference. Whereas if you want the strategy to be effective, this particular strategy we're looking at, you need to treat 5, 10, 20% of the units, because then the set of neighbors you reach are more impactful or more influential than the set of neighbors you would reach by treating a small fraction of the units at random, right? So we did, going from wave 3 to wave 4, we just no longer treat 50% of the units or 75% of the units, because we learned that was, useless, right? But we focused on the 5, 10, 20% of the units.
Yeah, any more questions? Yeah, I have a small question. So in your study, you have more than 100 villages, right? So you mapped all those social network for those households. So here, do we consider the link across different villages, or we just consider the links within the one village?
So we did track people moving from village A to village B in this location in the world. Whenever somebody gets married, maybe either the lady who gets married will go live with the husband's household. These are multi-generational households. And so oftentimes, not oftentimes, occasionally they will happen across villages. But when we ascertained these links, the vast majority of the links were within the village. And there were only a small fraction of people who would move from village to village across 8 years that we were tracking, right? Of course, there's also newcomer in the area, people who leave. So we did track all of these changes, and in our study we assumed, because they're small fractions, that they didn't have an effect. But the data is there to be looked at to see whether empirically there was an effect or not. We kind of did some simple analysis, and we decided that probably it didn't have much of an effect, and so in the paper is ignored.
Yeah.
But
Okay.
maybe it shouldn't be.
Okay, thank you.
So suppose you know a household that has very few connections are more at risk and can then benefit more from the treatment. Then what will happen to your strategy? Don't you want to target those in some sense?
You know, let me think 1 second. That's a good question, but it requires some minimal thinking here. So our strategy is to basically target more influential households or more central households, not just a bunch of households in the center, but starting from random places in the network to find the closest, somewhat central household, right? So, you know, if I had a network structure and you tell me, oh, what about these households at the periphery with very few connections, I could simulate, you know, the probability of that household getting treated. But answering you like off the cuff, like best guess, is that if you are a, you know, household that's very few connections and you're not connected to one of the central households, well, you are at risk of not getting any benefit from the treatment, right? So then the question is, you know, maybe a better loss function, a better optimality criterion would be what's the total probability of treating, you know, households that have the most likelihood of benefiting from the treatment. We don't have that, but you know, in an application you could have that, and then we would have to construct. Yeah, that's a very good question. Yeah. Does that make sense?
Any more questions? Okay, so if we do not have more questions, let's thank Edo again. Yeah, wonderful talk. Okay, now I think it's ending of this conference. Thank you all for get very tight 2 days, and I think we really enjoy a lot of wonderful talks and a wonderful view here. And in the future, truly hope we can get more events like this. And all of you are more than welcome to visit us more frequently. Enjoy the statistics, enjoy the view, and enjoy the good food. Yeah, looking forward to meeting you again in the future. Yeah, thank you. 然后常老师还要再说一句。
邓科刚才已经都说了，所以我就不说了。It's good to have you guys, and which I think the chat box has agreed to sponsor our meetings in future, right? So we'll work on with some thank you. Let's thanks the sponsor, right? And also for supporting this event. We hope we get supported in the future, and also all the volunteers. Yushan, Zhang Han, and all the people behind the scene. And also thank you all for coming from far, very far, long distance. Yeah, this I'm told by the sponsor, this is one of the highly very international conference that have been sponsored in recent period. Right? So they're amazed by the quality of the talk, and stay tuned and keep supporting us. We are still very young department, by all means, right? By all means. So please come to visit us and support us in various ways. And yeah, thank you very much for coming. Yeah, thank you. Yeah.
再次感谢各位老师辛苦了，近2天的这个密集的这么多报告。然后我们门口准备了一些点心和饮料，老师们可以稍事休息，然后去下洗手间。我们预计乘车的话是4点30分，在主